All right. Hi everyone. It's been a while. It's been 2 weeks since we last streamed. I was not feeling the best last weekend. Had some cold and preferred to stay indoors. And I usually stream from the office, so I couldn't come. Oh yeah, sounds good. Looks good. Okay, perfect. Thanks a lot for confirming. I was double checking that my mic is working too. Yeah. Sorry, I couldn't meet last week. Just not feeling the greatest. But this week I'm perfect, so we're back to streaming. I was actually waiting for like getting back. I had like a bunch of implementation things going on in my mind that I wanted to test it out. So glad that I could get back again. So yeah, I guess I do want to provide some like context on what we're gonna do today, but let's do some cleanup first. I have some thoughts in my mind, and then we'll get to the actual implementation. I'll start sharing my screen, and yep, I think the stream is showing correctly. Okay, so last where we left off was here where we finished implementing the ampersand and star operator, which means we can now work with pointers. We can dereference pointers. We can take address of pointers. However, we still cannot do pointer arithmetic correctly, because if you notice, our the plus operator and the minus operators are implemented as very generic plus and minus operators that work with integer values, and pointers would also be treated like integers, which they shouldn't, because pointer arithmetic is based on the type of the pointer. So that part we still have to handle, but as long as we're not doing any arithmetic, we can take address of variables and pass them around and do passing by references basically. So this actually wants gets to the point where we can simplify a lot of our implementation, meaning instead of having libc functions for every single thing that we want to do that's implemented in assembly, like the putchar function right now, we can actually take that away. We can actually start moving a lot of stuff into the C code itself, which is great because it gets like benefits of all optimizations and stuff that we'll be doing. So, I mean, not too many optimizations, but it'll all be together, and we don't have to handle too many special cases. So what I'm planning for today, is first thing to do is actually, if you look at our x86 libc, it currently has two functions, libc start and putchar. Libc start we cannot get rid of because it's like a special function that acts as an entry point. I mean, technically we could write this in C itself and maybe like insert a call to main and then call exit system call. However, the downside of that is we'll have to do like linking in some way, like we have to go and patch in the address of main. I guess we are already doing that. But there's really no benefit of writing it in C. So this, I'm going to leave it as an assembly function. It's like 5 instructions, who cares? But the putchar stuff, I think this we need to get rid of. So what I'm going to do now is I'm going to get rid of the putchar function, and instead I'm going to add a syscall function, which will be like a generic libc function that allows us to make any system call. And we will implement a syscall 6 version, so it takes up to 6 arguments. And that way, putchar can then just be implemented as a function that calls syscall. We can basically then at this point also start opening files, closing files, writing to files, or even like make network requests if we wanted to. Like we could implement a literal HTTP server in this the moment we convert we basically add a syscall function to our library. So that's basically what I'm going to do first, and hopefully that will make other things easier later too. So let's start by removing this, but before I remove this, let's add x86. See, my keyboard is again placed in a weird place. It's because the table where I'm sitting at, there's like a weird. Okay, I'm gonna sit like this. Hopefully this is fine. Yeah. Okay. There's like the table's leg is where I'm sitting. I should have moved the whole screen and everything to the right, but I placed it wrong, and now it's bothering me too much. And because of that, my keyboard is misaligned, and anyway, it's fine. So what we're going to do is we're going to implement a function called syscall6. It's called syscall6 because it takes up to 6 arguments, which also means all our syscalls have to pass extra arguments, but that's okay. I don't think that's too much of an issue. So yeah, let's implement this x86c libc syscall6, and so this one is going to get all its argument, including the syscall number on the stack, following our argument. Let me check if the draw.io still has what we need. I didn't. Oh yeah. Okay. So thankfully, all the way our calling convention works is our arguments are in the sort of like reverse order, or reverse, or whichever one you call it, like A is at the bottom, B is on top of that, C is on top of that. So we're going to have like 7 arguments on this stack, and they are going to be syscall number would be at the very bottom, and then every other arguments will be on the top. So let's first look at syscall 64 calling convention, and we need to know where to put the arguments. Yeah, so Gemini tells us they go in RDI, RSI, RDX, R10, R8, R9. Yeah, okay, so this one, instead of RCX, it goes into R10 for some reason. Okay, so there is some difference. Okay, let's start by start by first pulling the arguments. Do I need to set up the stack frame from this? Probably not, because we're not going to use any local variables. So let's just start pulling the arguments. We have total of 7 arguments, like 6 actual arguments to the syscall, and 1 argument for the syscall number itself. So that argument will be last. So we'll start with R9. And if I remember correctly, let's actually look at one of our generated functions and see maybe where the arguments go, like where do the arguments start, and that way we don't have to do the complex math for this. We've already done the math in our code generator. So obj dump, which function does actually have calls? I guess call.c, right? Yeah, this one has 2 arguments up to. Okay, perfect. So let's disassemble this. Now the problem is we do have executable generator, right? We do have like executables at the generator. The problem is if I try to disassemble this like this, it's not going to work, because it doesn't have, this is like an ELF, but it doesn't have any sections. Sections are, we do have programs, like there's like a, like we do have a program sort of like header which contains the actual instructions and everything, but we don't have sections. Now sections are not required by the loader. The section provides extra auxiliary information to stuff like obj dump, or to the linker, or to GDB, to know where, like how the instructions, how the data is organized. We haven't generated that, which means you can execute it, but obj dump won't work. But there is a way to make it work. If we treat the whole binary as a raw binary, we can make it disassemble those instructions for us. We just have to tell it everything about the instruction. So like the first thing I'm gonna do is just say bbin. That says it's a binary. I think it has to be BANARY, I think. Yeah, okay. So now it says I can disassemble this for you, but I don't know what architecture this is. This looks like an unknown architecture to me, because what's happening now is it's treating the whole file as a binary. There is no like headers or anything which you can decode from, but we can tell it. So we can tell it what architecture this is. That's usually done with the M flag. So I can say this is i386. That's Intel's architecture. However, we also have to tell that this is an x86-64. Otherwise, it will try to decode it by default as 32-bit architecture. And when I do this, voila, we have our instructions coming out of it. Now, there's going to be some junk at the top because of the headers being, like this is the ELF headers and everything being decoded as instructions. There is a way to tell the offset too, like you can actually tell objdump to start at a fixed offset, but that's okay. We will just skip over that. And this is basically where our instructions start, because you'll notice that this is the first move instruction followed by a syscall. So this is the libc start. And if you look at this is the putchar syscall. So, sorry, function. So that's basically where we have started. And the next function, there must be some global variable. Actually, this one doesn't have any global variable, so this must be the first function, right? And let's see what we have here. So, okay, so what this is doing is the push RBP, move RSP to RDB. This is like the stack frame setup, and then this is doing the space allocation for the local variable. And this is where it's doing. Yeah, this is where it's dereferencing the first argument, which is at 0x10 RBP. Okay, great. So that's, we know, is the first argument, and then it's doing the math with it and clearing it up. So, and then if you look at the next one, we'll notice that it does this and this, so 18 and 10. So we see that our first argument is 0x10, and then the next argument start from there. So we can just follow the same strategy here. So I'm going to say we can just directly move. We don't have to do LEA in this case anymore, because yeah, we're not doing any we don't have to take the address of the elements. This is just literally the values. So okay. So what do we do now? Move 0x10. Oh, actually, that 0x10 RBP would work if we did not push RBP, right? So usually that function does push RBP. This will, and then it does move Q RSP to RBP, right? So you'll notice, oh, sorry, RSP to RBP, right? And then it does 10 RBP. Now the problem is, if we use this offset, this offset is only correct if we do push RBP and then use this. What we are simply going to do is just not push it and start from 8, and then use RSP instead of using RBP. So this will also still give us the right arguments. So okay, so the first argument goes in R9. I mean, the last argument goes into R9. And then from this point onwards, it's just incrementing it by 8. It goes into R8. So X18 goes into R10. RDX RSI. Wait, no, this is wrong. Yeah, sorry, I just halfway through I decided to do, you know what, I'm not going to use hex. I can't do hex math in my head that correctly. I mean, I guess that was fine. We could have gone to 20 after this, but you know what, let's just do this correctly. Yeah, so there are more arguments than what we actually need for any of our syscalls, but 6 is what is supports maximum, so we are going to do 6. Okay. Wait, is it 54? It's 56. It's too early in the morning, I can't do math. Okay, and then the final argument, which is 64, goes into RAX. This is the system call number. And then we do syscall. The result of syscall already comes in RAX, right? Yeah, so we don't have to do anything, and then we just do return. So this is our syscall function. Let's just make sure I did the math correctly. 8, 16, 24, 32, 48, 40, 40. Okay, this looks correct. Okay, so we have created this x86c libc syscall now. Let's enter this into our syscall table, our global function table. So this goes into, let's do the tokenizer first. So tokenizer has our instruction, has our identifier table. So this is our putchar thing. We need to change it to syscall. So we had our encode keywords function. Let's just run this. Syscall 6. Hopefully it's 6 and 6, 8 letters. Yes, it does. Perfect. This is perfect. Okay. So we go here now. Okay, and I'm going to remove the putchar because we don't need that anymore. And this is still going to be %1, right? The index 1. Now, so the identifier table is done. Now we need to go to the global symbol table. Okay, this can be, yeah, here we have our global symbol table, and yeah, okay. So what we had done previously was just left a 0 here. What I'm going to do now is just going to put the address of syscall here, and we'll just do the offsetting in the code. So yeah, it already has identifier index 1, which is what we need. And then we just put this name. Okay. Okay, this is good. And now we just go to our execution area, which was this finalize. Was it in finalize? Okay, it wasn't prepare. So before we do anything, we did this, right? So what this is currently doing is it's calculating the address of putcat related to the new location and putting it. I'm just going to load the value from the table and patch it in. And this way we can, like, if we need to add more later, we can keep the same code. In fact, put it in a loop and just do it for other stuff. I don't anticipate having to add other functions, but you never know. Like if we decide to like implement our own like heap or something for malloc, it might make sense to put it directly into the table, but let's not. I mean, I'll try to avoid doing that, but there are some cases sometimes you have to do. Like if you can't implement the logic in C, you have to fall back to assembly. We might have to do it. So for now, I'm just going to So what this is currently doing is it's loading libc begin and libc size into RSI and RCX. Okay, and oh sorry, this one is just copying over the libc into the execution area. So that's great. And what this is doing is directly loading the address. So instead of doing that, I'm going to take the address of the global table. So what is it called? Global symbol table. What is the, oh yeah, okay. Let's get into RAX. Let's load the first value into RBX, and let's do the offsetting. So now what's going to happen is we're going to first subtract libcc begin. So we need that again. x86c libc begin RSI, right? We also need the, do we need the count? No, we don't need the size. Okay. We do need code gen buffer though. Yeah, we do need actually all of these. So this goes here, not in RBX, we'll do it in RCX. This goes here. Okay. So we loaded the start of the libc begin and we loaded the code gen buffer. And this one we can directly do on. Okay, so let's get the final address in RBX. So we do LE. Oh, we need to do some subtraction first. So we have to add code gen buffer and subtract libc begin. Okay, so let's subtract libc begin first. So subq RSI RBX. Okay, so RBX equals to RBX minus RSI is what we did. And then we can do this, right? And instead of this, it becomes RBX plus RCX plus 1. Okay, yeah, so what this will do is RBX plus RCX plus ELF header size and shifted everything, and this should go into RBX. And finally, we can just store this back in. So we can do this actually needed to be done exactly one. Okay, so we can do %RBX, comma 8 of %RAX, right? Okay, so we stored it back in. And this can now go away. Why is there a move from RDI to R14? Oh, this is the start of this. So actually, I'm gonna do this here before doing this. Okay, and then I mean, for now we don't need a loop because we just have one entry in the table, but we could add a loop based on what's the end of this. Yeah, we could do up to like global symbol table start, right? Yeah. It's okay. We'll just leave it as a single patch in now. Just put a comment here saying patch the global symbol table. Okay, and that's basically it. If I remember, I mean, if I can remember correctly, that's the only places where put char is a reference. I'm going to quickly check. I mean, there's the examples for obviously. Okay, why is it still? Okay, I didn't remove that, right? Okay, so this can go away now. Okay, there is one place, or did I not save it yet? There we go. I think they're all done now. Let's try to make, okay, at least it compiles, so there's no reference issues. Let's try, okay, so already complaining that factorial is trying to reference the putchar variable function, which it doesn't find. So let's change our factorial function. Factorial example, and so we have put integer here. What we're simply going to do is also implement putchar as a function. So what this will do is, I mean, we could use char here, but let's use int. Oh yeah, because it can be an integer actually. Okay, and then what we're simply going to do is, okay, it doesn't need a return, so we're just going to do syscall. Okay, so syscall 6 first of all, yeah, and then the first argument is the syscall number, which for write is Linux syscall list. I should have this pinned somewhere. Okay, write is 1, and then the first. Let's go to the arguments. Now I don't have to look at where is it? What? Now I don't actually have to look at the register orders because we are just calling a function now. So that takes care of everything. Okay, so we need count. Yeah, the last time we looked at this, I remember this was wrong. I'm going to look at, yeah, this was not size count. This is a typo here. It starts with int fd. So file descriptor, the out file descriptor is 1. The buffer is ampersand x, so we just pass the address of the variable x. We need the size count 1, and then so these are 1, 2, 3 arguments. We need to provide more x arguments, so 0, 0, 0. These are the rest of the arguments. Let's make sure our spaces are added correctly, because our tokenizer doesn't handle these. So okay, great, and this should work. Now we just have a syscall function added. Fibonacci has the same issue. But the fact that this compiles now, it's a good thing. Eventually what I'll do is I'll also support including header files, and this will go into a header file. So I mean, including putchar, put integer, some of the basic functions will add to a header file. Okay, putchar itself is, the example is failing. Short circuit. Okay, everything works. I think this did not work because it's supposed to print something, right? None of these printed anything. Yeah, maybe I used the wrong file descriptor. Let's see. Yeah, I didn't print anything. Uh-oh, okay. It's just one. So it's file descriptor, buffer, and then count. That sounds correct. Std out ft. It is 1. Okay, so that's not wrong. Syscall 1. Is right not 1? Right is 1. Okay, we must have made some implementation mistake in the x86 libc then. Let's see. Oh, this is a mistake. Why is there 2 RDX? Okay. So these are the 6 arguments. Oh, sorry. These are the 6 arguments. Okay. That explains it. Okay, now everything works fine. We get our hello world. We get our 120 from factorial. We get 13 from Fibonacci. Okay, great. So we made a quick change where now we just have syscall. So syscall is all you need in terms of like functions that are supported like without writing them in the language itself. And this can also let us do other stuff now, like taking inputs and writing out, which maybe we can test out, but for now I'm just going to, you can implement a get char function and then let the user input stuff, but that's okay. We probably trust this to work properly. Let's focus on the useful stuff. Okay, so next I want to actually fix some of our codegen like techniques. So let's look at this. Let's look at factorial quickly. Actually, factorial or Fibonacci. Let's look at Fibonacci quickly. So we have a recursive function that prints Fibonacci of 6, right? Let's try a bigger number. Let's say like 40, right? Fibonacci grows exponentially. Exponentially? Yeah, it does grow exponentially. So if we we'll notice that this Fibonacci function is taking a while to execute. Build examples Fibonacci. Yeah. Specifically, it takes how long to run? It takes 2.42 seconds to run. Let's actually make it a little bigger. Let's say 42. I want something that's a little big. Do we have a makefile target to just compile and not run? Oh, it doesn't. So just let's do make. Actually, we can. Do we want to do as part of all also do example executables? Let's do one thing. Let's call this run and then make a separate one, which is just example executables, and this can just depend on test. Let's just make test and run both phony. Make all. Okay. What phony does is it tells that this target needs to run regardless of whether it already exists. And this is done for stuff like name targets like test, right? Test is not really a file. It's not a target we are generating. But what happens if accidentally there exists a file called test in the directory? This will not run. And if it's fresher than, like, suppose I just create a file called test for some like debugging or something. What might happen is example executables might already be older than that test. It will think that, hey, test is already fresh, I don't need to recompile it. But that's not really a target in the sense that I'm generating something new. So what we usually do is make it phony, and phony says this needs to run regardless of what happens. I mean, regardless of the state of the file name test. Yeah, okay. So let's do make test. We just compile everything, and then we can separately run this. And let's time it this time. Yeah, I'm anticipating this being a little longer. Yeah, so it's taking 6.3 seconds to run. I also want to quickly make sure that the output is correct. So what I'm going to do is actually write a C version of that Fibonacci function, which we can actually, let's keep the same function. Let's also right, let's keep this, but it doesn't have put char, so we're just going to I think it's called put char without a underscore. Okay. Okay. This is taking a while to run, which is a good sign, but are the numbers the same? Okay, the values are correct, so we can be sure our Fibonacci works. So this is taking 6.32 seconds. How much does the... Actually, before we do that, I want to compile it without optimization. So let's do 0, and then we'll build from there. We'll make it better from there. Okay, so it's almost like it's 2.69 seconds. It's like how much times? It's like 2.5 times faster than ours, I think. 6.32 divided by 2.69. Yeah, 2.3 times faster. That's not bad to begin with. Like we have done horrible code generation, so let's actually do 43. Let's make the benchmark a little bigger. It's 4.33 seconds for the baseline version. Okay, and ours is 10 seconds. Okay, so this is like the right ballpark. Actually, let's also quickly check how much optimizations help, which is going to be a lot. Yeah, it's 0.75 seconds. It's almost like it's more than 10x faster than ours, which is expected. But that's good. Okay, so let's try to figure out like where our like issues are. If you look at the let's look at the dump of this, right? Like there's not many functions being called here. There's the main function, there's the Fibonacci function. So it's not a lot of points to debug. We could like do a perf on this, honestly, and that could also tell us the hotspots, but I'm guessing this probably won't have too many hotspots. So actually, let's check. I'm not 100% sure. So let's run perf on our generated code. I'm guessing it's going to be a lot of memory accesses and maybe the indirect function call, and we can try to fix that. Okay. Perf report. Yeah, so yeah, it's not very like, okay, this first of all, there's each Fibonacci is recorded as a separate function call, which is bizarre. Oh, I guess because it doesn't have symbols to tell it that, hey, these functions are the same functions. Yeah, okay, it has no annotations because it has no information about the yeah, it doesn't have any information about the executable, so we unfortunately can't get perf out of it. uh, we could generate a section and tell it where the instructions are and stuff like that, but I'm not going to do that because it's a lot of work. We could, however, try to extract a section out of it and then use obj copy to create an ELF externally for debugging, but that would be cheating, and I don't want to get the benefits of anything that's not being done by ourselves. So we will skip this. We will try to improve this on our own. So let's do obj dump again, and if you let's take a look at our functions, right? So we have start from the top. Oh, this is a lot of code, which it shouldn't be. How many functions do we have? So there's putchar, putinteger, which fine, they are only executed at the end, so they can't contribute to the execution time. It's the fib function itself, right? It has two comparisons and then two function calls. Okay, so we have to look for the one that has two function calls. Okay, I mean, if you look from the bottom, it's going to be in the same order. So this is probably main, because what this is doing is moving something into RAX. What is this last function? Oh, this is just the return. So there should be some call. Oh, no, wait, this is just garbage at the end, I think. Wait, that looks so much like a function though. Yeah, so this is happening because we're not disassembling properly. Like we're disassembling like at a bad offset, but let's try to, okay, just call, and call. I'm guessing this is the end of main. Because this is, okay, so it's loading 1A0B6. It's funny because these addresses are different. What functions is it calling? Okay, let's go from the top and find the address of main first. That will help us. So okay, there's a way to, like, actually let's do this properly. How do I tell obj dump dash in binary to start at a particular offset and set the virtual address? There is a way to tell obj dump like where to start. Okay, yeah, there's start address, which will tell it the offset for an adjust VMA. So start offset is the skip bytes at the beginning of the file, so we can skip over the headers, which I remember are 56 plus 64, so we can skip that much. So we don't need stop address, and adjust VMA shift the displayed address on the left. So let's start with the first one. We can say start address equals, you don't need equal, 56 plus 64 is surprisingly hard to do, 120, right? Yeah, okay. So what must have happened now is we start from the start function, so that's good. Our addresses are not correct though, so we have to tell it what the start address is. So let's first do read ELF to find the, like, what the actual virtual address is. Build examples Fibonacci. Okay. So this is our virtual address, right? This is where it gets loaded. So we have to tell it this too. I just don't know if they need to be like this is a long function. Let's do another one first. Let's do let's do a different one. Call maybe, yeah. Okay, so this not work correctly. It's still showing some junk at the beginning. What did I run? Start address 120. Okay, something is wrong. Yeah, I think I just VMA threw it off. Yeah, okay. So I think what's happening is the start address needs to be inclusive of like the VMA. So I think if we just do the same for both, that will work. Nope. So this is where you want from, right? 0F0. Let's actually do this then. There we go. Now we have everything correctly. So we have our addresses being printed correctly, and we have like these will now start making sense. So main is at 421, which is, sorry about that, 421. That seems wrong. Stuff is still not correct. Oh wait, maybe the wrong 421. This file is huge. Okay, oh, there's only one of those. I think the offsets are still wrong. 0F0. Maybe both of them need to be the same. Let's try this. Okay, no, this is wrong. So this was correct. Why is it doing this? You know what, let's do ELF again. Okay, so virtual address is A078. So this is where the whole program gets loaded. Yeah, this is a program header. So this is where the actual address starts. This is the actual virtual address. I think the start is this. So what's the math here? 0A7808F0. F0 minus 78. How much is that? Is this 120? Okay, this is 120. So what we are saying is start disassembling from here and adjust the VMA from here. Does this work? No. But let's check if this is correct now. So this now it's saying it's 421, A421, which is right. But let's check if 8421 is actually the address of main. It is not. So that wasn't correct either. This works correctly, but main is not correct. Yeah. Sorry, this is bugging me a little bit. Let's look at stats up. Skip bytes at the beginning of the file. Okay, there is a specific way to these flag interact that confuses two people. Of course, it's confusing me. Adjust VMA shifts the entire file's coordinate system. If you set it to 400,000, the first byte of the file, offset 0, is now considered at 400. Okay, this makes sense. The start address looks at the adjusted address. Okay, so if you want to use, if you just use this, you want the 10th byte, you would do, that makes sense. Yeah, I mean, that's basically what I did. So what we did is start. Okay, so we did adjust VMA at 07. Wait, why is this so weird? Why is it A078? What is 78 minus 120? Yeah, I think we need a mistake here. Okay, so now I know what is happening. We did the math wrong. So this should not be 78. This should be 00, and this should be 78. Okay. There we go. So now the instruction starts correctly. 4 to 1. And 4 to 1 is the main. Perfect. Okay, this took a while, but we figured it out. Great. Okay, so let's look at the Fibonacci function that we've generated. This is our main function. First calls the Fibonacci function, which is here, and it, what is, oh no, first it passes the outer. This is the put integer function. This is the Fibonacci function, and then it moves to b, which is the argument 43 in this 42 whatever we're passing, and then it calls. So this is the function we are supposed to look at. Why is this never appearing? Okay, let's do A2D3. For some reason the search wasn't working. I guess because 0x. Okay. Yeah, so A2D3, this is where our function starts. This is what happens when you don't have sections. Okay, this is where functions are. Okay, so this is our actual Fibonacci function. And you'll notice that there's a lot of, first of all, there's a lot of push and pop, which is bad. This is like unnecessarily moving values through the stack. What we've implemented is basically a stack machine, right? Like when we have sub-expressions to evaluate, what we're doing is we're pushing the value, that sub-expression first pops its arguments from the stack, computes the result, and pushes it back again. And this is causing redundancies like this. Like this is slow, like you're moving from RBX to RAX by doing 4 instructions, whereas this could be done with a single instruction. And all of these 4 instructions have tremendous amount of side effects. Like they're updating RSP every single instruction. They're writing to or reading from memory every single instruction. And this is very wasteful. So that's not just the only reason though, by the way. There's like, everything is going to memory. Like if you have one instruction, like say not of x, we first compute x, we put it on the stack, then we pop from x, we compute the not, and then push it back again. Like why does it need to go to memory if we just have one argument to a function. Like if there are two, yes, sure, I understand, maybe like you need to free up some registers and you need to do that. But when there's like just one argument, like return x, right? X first gets computed, gets thrown onto the stack, then gets popped by return, and then gets returned. It's a lot of like wasteful computation. Look at this. Plus on top of that, we have these no ops created because of the instructions themselves, like the sub instruction stuff. We made them fixed sizes and padded them with no ops. All this is adding up and it's causing a slowdown. So we will fix this. I want a more clean code generation where we don't like do the stack machine thing. So this is a heavy change because we're going to have to change the way our entire code generation works. But it's not that hard. So what I'm simply going to do now is follow a new convention, which is all the result of every expression will always be in RAX. Actually, before we decide whether it should be in RAX or RBX, I want to see what division takes its arguments in. So we had this, right? Yeah, we're looking at IDivQ. Yeah, IDivQ is what we use. I just want to quickly check IDivQ, what order it takes. Type. So IDivQ here divides dx by edx by the source operand divisor and stores the result in this. So yeah, the divisor goes in whatever register we pass here, which means the first argument is implicitly in RAX. Right, so the convention we're going to follow now is for every expression, the return value is always going to be in RBX. And wait, but RBX then would cause returns to have to move. Should we optimize for division or should we optimize for returns? I guess returns appear everywhere, so we should optimize for returns. Okay, so the convention we're going to follow is every expression puts its result in RAX as opposed to putting it into memory. And the benefit of this is if a particular operation only needs one argument, it's already in RAX. It can just do whatever it needs to do, update RAX, and done. There's nothing else to be done. If it needs to like compute a second argument, then it can temporarily store RAX on the like stack, and it doesn't have to push. For that, we'll just like use our regular stack like local like allocation, which we have done for local variables anyway, and that will like keep our code generation very, very clean. So let's start by doing that. Okay, let's go to parser. So we have parsed u, parsed. Let's go to parse expression because that's all that we care about. Our expression statement, parse expr. Oh, parse expr is in a separate file. We created a whole parse expr.s. Okay, yeah. Okay, so this is handling all our parsing. So this is assignment. We will get to assignment later. 14 is assignment, right? Yeah, 14 is assignment. Let's go from top to bottom and fix each one of them. Okay, so this is handling ampersand. Okay, so there's other part to it too, which is remember when we have identifiers, they can be both L values or R values. So when you're parsing an expression like this, let's say we have a equals to, actually let's say a plus 5, right? Like when we're doing this, when a is being parsed, we need the value that a holds, right? Because we want to add it to 5. But when we do a equals 5, we need the address of a. We don't want the actual dereferenced value at a. And it's hard to know what we need just when we are parsing a. Like in a complete, like a multi-phase parser which has an IR, you can actually just look at the type of expression and know what it is. But we haven't parsed it yet. We don't know what's going to happen with a. So should we generate the address or should we not generate the address? And in the past, the way we handled this is we push both the address and the value on the stack. And then the next expression, the parent expression, will use whichever one it needs. This is obviously wasteful because we need to pass around 2 values per expression, and most expressions don't actually have an address. So why are we doing this? So for this, what we'll do is we'll follow a convention where variables always return their address immediately. Now, if the parent expression wants the value out of it, it will convert it to an R value by dereferencing it. The problem, however, is the parent expression doesn't know what kind of like sub expression it has. Like when you're parsing the, like for example, if you're doing a plus b, when it reaches the plus, it doesn't know whether the first a was a variable or it was this. So there's no way for it to know like should I dereference this or not dereference this. And to fix that, what we're simply going to do is we're going to follow convention. When we do get parse, when we call parse expression is actually now in RAX, in the compiler, not in the generated code, going to return whether the value that's stored in the generated code in RAX is a L value or an R value. And if it's an L value, the calling code can then promote it to R value by doing a dereference. And we will write a small helper utility for it, which will just say, make sure this is an R value and not an L value, which will just dereference it. So that will make things easier for code generation and also like help us, right? So we'll actually write that first. This function that does the L value to R value promotion. So we will call it, oh, this should not be here. You don't need to be global. Let's just say promote to ensure R value, because it's not necessarily promote, it's just checking. And this one, by the way, needs the argument in RAX too. So like the flag of whether it's a like a L value and R value. And what we're going to convention we're going to follow is 0 is R value and 1 is L value, right? Okay, so let's do this. So how do we compare? I'm gonna check if it's 1, right? Okay, so if it is 0, then we jump to end because it's already an R value. If it's not, we have to first generate the code to turn it into an R value. And for that, we need to go to our and write some generation. It's very simple. It's just going to do move q RAX into RAX, right? Just takes the address and moves it into the actual dereference register. And okay, so it's just this 48-8B00. So this is what we generate. Move Q. Yeah, we can just store a 32-bit constant, right? since it's ending in 0, we don't have to put that 0. Okay, so this has promoted the L value into an R value by dereferencing it, and at this point it should actually set 1 into RAX, right? So this way it will know that, hey, this is an R value now. Okay, so with this utility function, let's start implementing our we'll come to, we can do assignment first. Yeah, let's just do that. Okay, so right now what it's doing is it parses the first expression, and in this case then it checks if it's an assignment. If it's an assignment, it calls parse expression pre. Now the first thing to do is the value that came out of this expression, the first parsing, must be in RAX. Before we call this, which will probably clobber RAX again, we need to store the first value onto the stack. And the way we are going to do that is first grab a stack slot and then store it in the stack slot. So we will do that by adding a utility function called get stack slot. Okay, and this does it by just whatever we did for variable declarations, right? Yeah, parse variable declaration. Here. So take current function slack slot into RBX, and that's it, basically an increment that by 8 and store it back. Okay, so this goes here, current function slack slot. This is going to be a return value, so I'm just going to do move q, actually I also have to do the math for this. Okay, okay, so we just obtained one stack slot, and we added it to, yeah, and we returned it. Okay, so okay, let's write assignment. So we have passed our first sub expression. So now in this case we don't need to do L value to R value promotion because we need it in like the L value. So we don't do any L value to R value promotion, directly store this value onto the stack slot. So first we move RAX into RCX. Actually no, we don't need RAX because the value is already there. So we simply do call q get stack slot, right? Now we need to put the current value of RAX into the allocated stack slot. So let's write that, move q RAX into, let's say 32 RBP, right? It's all RBP relative, but it'll be like negative RBP. Oh wait, let me check. Yeah, we had to do -8, not +8. Wait. catch that in time. Okay, so the number is already negative then. So we just have to, let's test this out. Okay, so these 4 instructions will store, where is 20 coming from? 0x20, how is that encoded here? I think it's using like a, let's try to change this. Yeah, it's using a 1 byte encoding for it. I need this encoding to be more than 1 byte because eventually we'll have 256 or more stack slot. We want to be like sure it doesn't create this issue. Let's see. I mean, technically we could do like if condition and say if it is less than 256 to something else, but maybe I can do this here. That doesn't work. Oh wait, I did not compile. Oh, okay, I'm gonna ask Gemini. To encode the instruction move q rex to offset of RBP where the offset is negative and I need the value to be a 32-bit offset. Wait, how did it work for address of variables then when we did LEAQ? So identifier, right? There was 2, yeah. No, this was pass pre1, yeah. Identifier integers. So if it's identifier, it's parse identifier expression. Here. Parse identifier local. Yeah, this one. Oh, it's doing the LEA, so that's why it gets to do a annoying. I don't want to do an LEA. I want to do a, okay. To encode this with a 30-bit offset, you need to construct the instruction piece by piece. The REX prefix, the opcode. The REX prefix we already have from 48. Yeah, 48, 89, that looks correct. The mod RM byte. This indicates that the 1 in here in the first 2 bits ensures 32-bit displacement. Instead of 45, it just needs to become 85, and that will take a 32-bit offset. Okay, I think that works. So why can't I do this in GSM though? Let's actually ask. Is there a syntax in GSM? Oh, disp32, not D32. Nope. Well, it just lied to me then. That's exactly how I did it. Oh. That did not work either. The binutils.js doesn't support. I mean, I could also try to include, it's fine. I'll just do 85. And I will just trust it here. Okay. Okay. Nope, not this. What was it? And this one, I'm going to change it. The annoying part is we still have to encode it in 7 bytes, which is kind of wasteful. Like 7 bytes to just store a temporary like register on the stack. The benefit, however, is that it's not changing the RSP, and it's not changing it's not accessing memory. I mean, it's accessing memory, but it's not that bad as like just doing a push pop. The push pop would be like less instructions, but this is somewhat better. Let's try it out, and if this is still slow, we can do something else. Okay, let's encode this. So this is going to need 4, 85, 89, 48, 2. And then we already have our thing in EX, right? The slack slot is in EX, a negative number, which we will store at 340. Okay, and then seven. I'm thinking of making this into a function too. Yeah. Stash value to stack. And we can also do get value from stash. Okay. Remember, however, that this takes it in EX, so this will also take it in EX, and it's going to do the other side. This did not work for some reason. I can't get it to work. But this time we're going to move it into RBX, not into RAX. And the reason for that is the second argument, like the use cases for this is when the first argument needs to be stash. When it gets out, it shouldn't clobber the RAX, which contains the second argument now. So you're going to move it into RBX instead of RAX. And it's so this is probably going to have the same adjustment need to be done, which is instead of, so this will be 8D, same mod bit. Okay. Oh, yeah, I think this is fine. This is fine, yeah. Yeah, so the stack slot is again in here. which means we also need to, in the calling function, we need to like stash this we need to stash this value. Oh, we haven't changed the associativity of, so this is currently written wrong. This is currently doing the associativity right to left. Associativity should be left to right. We will fix this later. This to do still stays. Okay, so we need to allocate a stack slot for this now, which means we need to do. So what's happening is the stack slot that we allocated in the generated code needs to be stored somewhere, which means we need a local like we need a local stack slot to move it. Stack slot for the temporary. Okay. And so where are its returns? Here. Equal to leave. Okay. So we call got a head out, great to listen. Oh yeah, thanks a lot for joining. Hopefully by the time you watch this video again on YouTube or something, we would have some optimizations done, and hopefully we'll have some good performance, at least comparable to GCC O0. And yeah, thanks for joining. I'll stream again next week, so we can continue there. Okay, call get stack slot. We need to store this into the assigned stack slot so we can retrieve it later. Yeah. And then we immediately also call stash. What is it called? Stash value to stack. Stack. Okay. And now we can parse the right hand side. And this whole thing gets changed now. Now you might think, why can't I just move from RAX to RBX as opposed to putting it on the stack and removing it? And there's a specific reason for that, which is we don't know what happens inside this parse expr pre. Like this might also need to use RBX or RCX or whatever. I mean, a proper register allocator, what it would do is it would first generate an IR and then look at how many registers the inner expression is using, and then just like try to allocate into registers first. But we don't have that much like forward look ahead into the expression, so we'll just stash it onto the stack in the generated code. But it's still better than doing pops and push. This will be similar to what GCC O0 does too, so it shouldn't be too bad. Like every temporary goes onto the stack, that's fine. Ideally, we should be reusing stack slots too. Like instead of getting a new stack slot for every expression, we should return like stack slots too. And that's possible too. We can do that optimization later. The good thing is we make this change once and then we don't have to touch this part ever again. The only thing we have to touch is the part which gets and gives you stack slots back. So we can actually reuse stack slots later too. I mean, I'll have to call the return stack slot function, but that's fine. That's not too bad. Okay, so let's say parse expr pre gets called. And now we need to retrieve the value. So we say call. Oh, no, wait. So the right hand side needs to be promoted first. So we say call ensure R value, right? Because the right hand side is being assigned. It's not being um, it's not being written to, so that stays as is yeah. Okay, so the right hand side is an RAX, um, and the left hand side needs to be popped up. So we say call, uh, what is it called? Stash, get value from stash. But we also need to tell it where the value is. So this goes into, right? So now we have our second into RAX, and this now all can be solved. Okay, so this can all be cleaned up, but we'll do this later. We simply do the storage now, which is simple as move. The first argument isn't, so it goes RAX comma RBX, right? This will just do the store for us. That's all we need to do. So this is much simplified now. It's just 3 bytes encoding for this. I'm going to keep this because this still needs to be done. Right? Okay, and this can all go away because there's no assignment, no null pointers to be pushed, nothing like that, and we can simply go to the next one. The only thing that needs to be changed is we need to tell it what the like whether we are returning an L value or an R value. Uh, this is a little annoying. So let's think about what we have in RAX. We have the address in RBX. What is assignment supposed to return? Assignment is supposed to return so let's do some clever math here. Instead of having to use um, stack slots again and again, we can acquire one stack slot in the beginning, right? Yeah, so let's do that here. Right? So we get a stack slot in the beginning and it's an array. And then we can do great. Okay, so the value is in RAX. So the annoying issue now is the address is in RBX. Yeah. Which is what this expression is return anyway. So we have to also generate move RBX to RAX. Yeah. because the return value of assignment is not the value, it is the address of where it was written, because it's still an L value. Yeah. To be fair, like the L values will be now we can have an address of outside, which is what I'm thinking is everything under assignment, like if we look at the precedence table, doesn't require an L value, so we could actually return just the L value. Right, like assignment is here. Yeah, there's nothing below assignment. So once assignment has been passed, you can just return the L value and no one would care. Actually, nothing, we don't have to return anything from 14. Like once assignment is done, there is nothing you can do except for parentheses. When we have parentheses, that might need it. Not supporting parentheses yet. I mean, eventually assignment has to be converted to a recursive function because it is right to left, not left to right. And currently we've implemented as left to right. So what will happen is it will need the address of the outer one. Fine, let's just do it the correct. You know what? For now, I'm just going to move Q. Actually, this is fine. So we don't need to do anything right now because for the next loop, the stacks, like the value that's stashed. Oh no, this is going to cause an issue. I hate this. Okay, so what we do is we actually move this here, right? No, but we also have to check if it is assignment. If it's not assignment, we should not stash it. God, I hate this. Trying to optimize, trying to like generate least amount of instructions to do it correctly, and I don't want to like, since the if like we are implementing as left to right associativity, which means that the address that we'll be writing it to is always the same. I don't think it matters. I'm going to just move rbx to rax and return. So yeah, I'm just going to generate this too. It's fine. It's not a big deal. Sorry, this is annoying, I know. Okay, so what this will do is it will make sure that we store the value at the address and then also move the address into RAX for the next instruction to work properly. And then we will just say that this is actually an L value, which means we move 1 to RAX. And this also needs to go here because assignment always returns an L value, and this will take care of it. Okay, this is fine. So assignment has been taken care of. Let's go to 2. So this is ampersand, which is address of. Now address of is very easy, because what address of does is you have, it must already be an L value. All it says is it's an R value now. No code needs to be generated. Taking an address of does nothing, right? So this actually generates no code. Generates no code, just promotes, just tells the calling code, just turns the L value into an R value. So we don't need any of this. We simply say move Q Yep, this is all it does. This is great. This is star. Now star is a little weird in that star has to dereference, which means it must be an R value. It must dereference it and then give it out as an L value. No, let's think about this. Let's think about this. Star is the opposite of ampersand, right? So it gets an R value, which means it should ensure that it's an R value first. But it shouldn't actually dereference, because a star could also mean that later we have an ampersand on it or an assignment to it. So we can't really actually dereference. We just, okay, this also does the opposite of it. So generates no code, just turns the R value into an L value, right? Yeah, so this goes away. We just do move Q $1, RX. Yeah. So what this is saying is, yeah, I know you had a pointer. But I'm going to make it into like a reference. Oh, actually, before we do that, we need to make sure that it's R value though. So yeah, because this itself could be an L value, right? Like this could already be like a address of a variable. So if it's an address of a variable, first get the value at that, and then treat the pointer itself as a L value. Yeah, okay, this is correct. So if it's an expression like a plus b, where a and like a plus 5 where a is a pointer, this will not do anything. It will just say that, okay, but at this point treat it as an L value now. Okay, this is good. And these are fine. Nothing gets generated here. Pre1 is a little weird. Okay, so we have token L parent for function call. Yeah, so let's not change function call too much in terms of its implementation, but like we have to update it now because we don't use any of those. Like, yeah, the arguments need to be, as soon as we evaluate an expression, the argument needs to be moved onto the stack. Yeah. Function call is handled separately. In identifier and integer. Okay. So if it's an token integer or token identifier, this goes here, pre. Yeah, we'll handle them later. So pre is where all the operators get handled. So we will handle this next. Yeah, these are a little complicated. We'll handle them next. Parse expression pre-finish. Pre-12 was again similar. It just generates the Boolean versions. They will be handled next separately. Yeah, the reason we did 12 separately was because they have short circuiting, which is annoying. I think 11 also must be handled separately. Yeah. So the short circuiting makes this thing very hard. I struggled a lot with this last time. Okay. Yeah, parse integer expression. So okay, parse integer expression is also fine. All it does is moves the constant into Rx. and that's it, and says that this is an R value. Okay, this is fine. So actually we can just leave it exactly the same, except just remove the push RAX. Yeah, so this is all we need. So it will be 48C7C0 and then a 32-bit value. Since it's an integer, it's fine for it to be a 32-bit value. Okay, and this goes away, this goes away, we don't need to push any null pointers anymore, and this just becomes 7 bytes, right? Yeah, great. And then we also need to tell it that, hey, this is a R value. 30 continue. Okay, and yeah, this is fine. Expression local. What this is currently doing is loads the address into RX and dereferences it to. We don't need these. So all it does is 48AD85 and then the constant. This is not required, this is not required, this is not required. This just becomes 7 again. Yeah, loads the address into RAX, and now we have to say it's a L value. That was an R value. Okay, jump expire pre-continue 0. We have to check what this does, by the way, later. For global, it's the same again. We just move the values and then we do nothing. It's just an 8-byte address, which is here. So this goes away. This just becomes how much? 8 plus 2, so 10. And thankfully it's already in RX, so we don't have to do much. Okay, and then we just have to tell it that, hey, this is a L value. Let's check what parse expr pre-0 continuous. Okay, just return, so this is fine. Okay, let's go to the top and handle everything again. Okay, so we handled 14. We'll go to 2, also we did. 1 also we did, but the function call needs to be handled. 0 we handled. Okay, let's do pre now. Okay, so we have current precedence. Okay, save tokens. Okay, current operator entry, yes, and jump instruction address. Why do we need a jump instruction address? What's the jump instruction address for? I think this is not being used, jump instruction address, because there's no jump for like regular Boolean binary expressions. It's only required for the 12 and stuff, right? Let's check. Yeah, this is only being used in 12. Unless, oh yeah, 12 is being called from here, so they kind of share the starting setup. Okay, fine, we will use another stack slot, minus 48 RBP stack slot for first expression. Actually, let's fix that R14 thing too. Let's only allocate if we need it, right? This is causing unnecessary stuff. Yeah. Yeah, let's allocate a stack slot only if we need it, which is if there's an assignment, which means it will allocate a new one every time, but that's okay. Yeah, it's better than allocating it unnecessarily. Not making the stack too big. Okay. Okay, stack slot for first expression. Okay. Now, let's see what it does. So, this needs to change. So move RSI into RBP. What is RSI? The precedence, okay, that moves into minus decrement precedence and call the parent expression. Okay. Now, move RBP into RSI, loads the precedence and checks what to do with it. And let's handle these later. Let's try this out. So it calls get token. At this point, it's all, once it has reached these precedence, oh, it can still need an L value. So we shouldn't perform L value to R value conversion unless we are going to do some math with it. Okay. Right. We shouldn't do that unless we are willing to promote it. Right. So RAX here contains, okay, but before we call get token, we have to stash it. So we need another stack slot. Actually, we can use the 48 one to, yes. Value category of the first expression. Okay. So we did parse expression pre, we immediately store the value category into minus 48 RPP. Yeah, so this we can retrieve later. Okay, now we do the call get token. We check if it's a binary expression. If it's not, we error out. If it is, we store the operator. Yeah, RAX here contains the entry of the yeah, 32 is current operator entry. Okay, so before we retrieve the current operator entry, we should ensure that the value is first converted to an R value. So we do move Q minus 48 RBP into RAX, and then we call ensure R value. Okay, so now we have and then we move Q minus 32 RBP to RAX back again. Okay, this is fine. Actually, before we do this, let's store the value too. So we say call get stack slot, and then we call stash value to stack. Let's just generate the code for all of that. Yes, this is great. And now we can load it back again. Right? Yeah, so it takes the current operator information and this starts code generation. Oh, this is first comparing. Oh, no. We need to first compare. and make sure that this is for us. Yeah, okay, so this we haven't finalized yet, so this is not actually done yet. Let's move this here for now. This can go. Okay, so what this is doing is loading the precedence, comparing the precedence with our precedence. If it doesn't match, it skips. Otherwise, low. Okay, before we do this, now we need to stash the value. So yeah, what did I do? Sorry, oh god, caps lock turned on accident. Okay, and this goes here. Okay, so what this does is gets the precedence out, make sure that it's an R value, because at this point we need to convert. We get a new stack slot, we stash the value on the stash. Perfect. And then we decrement RSI and call parse exp pre. Okay, now we have the first expression in RAX and the first expression in RBX. No, we need to get it out first. So we again do, oh no, we first need to make sure that the second one is R value 2. Yeah, because it could be a variable. So we ensure that the first and the second one both are R values, and then we need to load the value back. Oh, we never stored the thing here, so this also needs to be stored. The stack slot we had gotten. Okay, so now we have the first one in RPX and second one RAX. Okay. And actually now we're going to clean this up a little bit. We don't need this much code generation for this, right? I'm going to rewrite all the binary operators. How many are there? Oh god, there's a bunch of them. It's fine. That's fine. Let's go back and check what order they are in. So they are, first is token star. Right, so this will do RBX times RAX and store it in RAX. That's it. That's all we needed to do for multiplication. It's easy. Okay. No zeroing out, nothing needs to be done for this. Next is divide. Okay. So divide is a little tricky because I div q. So they actually need to be swapped here. Let's look at rdefq instruction again. Sign divide. So what this does is divides edx eax by the divisor. So there's a way to like sign extend eax into eax edx. Wait. We want the 64-bit one. idefq 64-bit. in 64-bit. Yeah, RDX, RAX. Okay, there is a way to promote it first. How to sign extend RAX into RDX colon RX. Sign extend RX and RX registers CQO, convert quad word to octo word. CQO instruction takes the sign bit and copies it into every bit of RDX. Okay. The annoying issue for us is the first argument is in RBX, not in RAX. So we have to do some swapping around. Is there an instruction to swap RBX and RAX? I hope there is one. Yeah, okay, exchange. Okay. I mean, I guess that's general reason. Okay, so what we'll do is exchange RAX, RBX, right? Then we will sign extend RAX, CQO, RAX. Well, CQO already does RAX, it's an implicit instruction, right? Yeah, just CQO. And then we do itivq RBX, and this will store the value in RBX, which is again annoying because the result needs to be in RAX. Then we do move q RBX to RAX. Yeah, so div is a little long, but that's okay. Actually, idivq puts the result in RAX or RBX and stores the result in RAX. Perfect. We don't need to do this. So this is gone. For the modulo, we'll have to move RDX into RAX. And this already returns an R value. So it's not too long either. This is not too bad. Okay, so division is done. We have percent. So percent is exactly the same, except it also needs RDX into RAX. Perfect. What's next? We have plus. Plus is easy. Just do RAX, right? Is one of these registers instructions required RCX to be zeroed out? Not right now. That's okay. Add q RBX into RAX. This takes the first arguments, adds it to second one, and stores it in the second one. This is fine. Sub is gonna be an issue. Token minus. Yeah, so minus is gonna be, if I do this way, it does second minus first, but if I do this way, the result is an RBX. Then I have to move. Yeah, this is for sub, and then less than. Okay, so less than is compare. How did we do less than before? Set LE, right? Yeah, set L. So it compares and then set L. What's the order of this though? I think it'll be RAX, RBX because it follows the same as subtraction. Okay, yeah. Set L. This puts register, yeah, in RCX. Yeah, okay. Let's check. Wait, is there a way to... Does settle take an argument? It does. So it doesn't have to be CL. Can I do %AL? Yes, but it will not clear the higher value, so I need to somehow clear it. there a way to zero out higher bits of RAX, keeping AL intact? Maybe we don't need to do it. Like, for comparisons, we could just use. It's not gonna work. Zero extension or a bitwise, and yeah, let's just do this. It's fine. Does set L work with AL? I should make sure. If it's not, then we yes, it works perfectly with AL. Okay. I don't know why we were doing CL then. Yeah, I immediately do move BCL. Yeah, this needs to go after every comparison instruction. So compare, set, and then move. Okay. This was less than. Next is greater than. Then we have greater than. No, we have less than equals. And then we have equals. Now equals is, yeah, it should just be fine. It will be the same. Just set E. Not equals. Perfect. And that covers all of it. I think it should be IML, right? Yeah, have to use, no. Yeah, you have to use IML with RBX. I think it's implicit again. Oh, it's unsigned multiplier. This is integer, so I have to use integer. IMLQ takes 1, 2, or 3 operands. This is fine. Okay. 28-bit result. Yes, only in one operand form. Okay, this is great. This is fine. We just change this to IMLQ then. Because this, okay, what's the 2 operand form of IMLQ? Okay, 2 operand. IMLQ RCX RAX, RAX equals to RAX times RCX. This is perfect. And because it's multiplication, the order doesn't really matter. Okay, this is good. Okay. What I'm gonna do is I'm gonna copy these over into the table first. Okay. Now we're going to copy these over. So IMLQ is just here. This is div. percent exchange sign extend def and then move. This is the longest instruction we have. It's not too long, it's some number of bytes. Add sub. This is sub. These are all the comparison ones. They're all 9 bytes now, which is annoying. Alright. Okay, so what this is now doing is we have to change the entries now to also include the length. I don't want these instructions to be like unnecessarily long and padded with no ops when we don't need them. So yeah, I'm going to add another quad, which is the current quad is a precedence. We're going to change it to how many bytes do I need? Let's compute this. 8 is too short. No, actually 8 might work. No, this is the longest one. So we have 6 plus 2, 10. Just do 10. Who cares? Yeah, like a long and a short should fit. These are 9 each. Yeah, this works. Perfect. Okay, this works. So it's what now? 8 plus 8 plus 8 plus. Should I make it a multiple of 8? Does it really matter? Nah, it doesn't. So 24, 34 bytes. PTOS. Where did I find it? Not here. Oh, here. It's 34 now. Okay. Now let's fix each of these entries properly. Add the. How many this is? 1, 2, 3, 4. We have 10 bytes worth of space. So first is going to be a long C3AF0F4 8, and then we need to fill up 10 bytes. So we're just going to say dot space 6. Yeah. Divide requires 1, 2, 3, 4, 5, 6, 7. So I could make this 4 and that would be fine, but 4 and 12 that would have been easy, but this is okay. Okay, so what's the way to do this? I think I can do this as a quad, right? Yeah. FP F7 4899489348. Perfect. And these are 1 2 3 4 5 6 7, which means I need a space of 3. Okay, these are occupying all 10, right? Yeah, 6 plus 4 10. Okay, so this one I'll do as a quad followed by a long. So the first 8, which is 1 2 3 4 5 6 7 8. Then no space. Needs a full 10. Okay, plus is only 3 bytes, so that's good. Just do a long for it. This is exactly what we did here. Oh, that was actually 4, so this is fine. 0 0 D8 0 1 4 8. Perfect. Okay. Minus is 6, so we can just do it as a single quad. These are all occupying 9. So 9 is going to be done as a quad followed by a... Actually, let's see how they differ. So these instructions are the same. All they are differing in is the middle byte, right? So let's do a quad, no, long byte long. Yeah, that will make it easy. C0 B6 0 F CC. Yeah, okay, so this is good. And then we finally have a space of 1. Right? This can go away. And wait, where's the precedence? Oh, this is the precedence. So just copy this over, paste it here, remove this. Actually, let's paste it everywhere first. Okay, let's do the cleanup. What are these for? So this is identifier, this is precedence, this is length, and then just a final entry to keep everything clean. Okay. Amazing. Here it is. The 11, 12 has to be handled separately, but we'll do that after. Um, drink some water. Actually, yeah. Okay, so we have called both the expressions now. This has loaded the value into RAX. Now we need to just generate the code. So this can all go away. We first move the start of the address. So that is 24 RAX into RSI. Move Q R14 into RDI. We're just going to use the copy instruction, whatever it's called. And then move Q16 RAX into RCX. This is just the count, and then what is it? Move SP, rep move SP. So this just copies over the right number of bytes, and we just need to, oh, and RDI is already shifted, so we don't need to do anything. We just move back RDI into R14. Perfect. This is the easiest code generation. And then since we have done the operation, we would do because this will ensure that it's in a R value, and then it goes to pre-next. Pre-next calls get token. Yep. Wait, where is the first one stashed? Here, and yeah, and then we're ensuring it's R value, so this one will already be an R value, and we'll be fine. Perfect. This is good. Okay, now let's handle these. This is OR. This actually doesn't need to do too many changes. What it's doing is oh wait, we have to restore the, yeah, when we do the comparison, and if it doesn't match our binary operator, we have to ensure that the value category of the first one is restored. So yeah, if you pass the first one here, it's stored into 48 RBP. Then we call pre-next. Oh yeah, so instead of putting it into RX, what we should do is we should just do move Q0 into minus 48 RBP, and this finish will then do minus 48% RBP to RX. Yeah. This is better because this will ensure that then the next one will also have the right value because it's loading it from this, right? So yeah, it shouldn't reuse the very first expression's value category. And if this jump goes back, it loads the next token, and if it's not a binary operator, it jumps to pre-finish, which would then restore the last one from RAX and return. Okay, thank God we handled this. Otherwise, it would have caused enormous issues. Okay, so 12. What does 12 do? Calls get token, stores the token, compares it to be RAX. Has the first expression's value already been stashed? Not yet. Has a stack slot being allocated? Also not yet, because literally what we have done is just call the first one and it stored its value category. Okay, fine. Okay, so since we have realized that this is a OR expression at this point, we need to do a few things. Oh, this one is doing generate booleanify of the first expression, and it does all that nonsense. Okay. This is fine, we'll do it. Let's just ensure R value first, right? Yeah, we don't actually have to do operations on this, so we don't probably need to stash this value. It does one at a time. Yeah, the good thing about short circuiting is because you're not actually doing an operation, we don't need both the values at the same time. It only generates a bunch of like jumps. So this is good. We never have to touch RBX, which means we never have to stash anything. Okay, so this will ensure that it's converted into an R value, which is great, and then generate the booleanify of the first expression. So this can go away. We don't need to do pop RBX anymore. It just does test RX, sets AL, moves it to EAX. This is basically doing, yeah, A equals A. Okay, and then this is fine. Pushes RAX, this is not required. Why are we doing this? Oh, this is the truthiness of it. That's fine, you don't need it. Actually, we don't need this either, because the value is never required again, right? Yeah, this is fine. So we do test RAX set NEAL. Actually, set NE is also not required. We just do a comparison. Why did we do it this way? Okay, we will fix these later. Let's just write the assembly instructions first. Okay, so what we have simply done is checked if the RAX is true or false. If it is equals, meaning it's 1, yeah, E is not 0, right? No, E is 0. Yeah, okay, yeah. If it is 0, then continue, else should be jump on 0. I mean, it's the same instruction. I'll keep it E for now. Yeah, if it is 0, then continue. If it's not, then skip forward. This is fine. And then we say, we pass the second expression. So this one is loading. Wait, why is it loading 10 and not 11? Should load 11. How is this even working? I'm not doing 12 right now. Yeah, this should have been 11. Happens to the best of us. Okay, so this one calls 11. Again, these values go away because we already have it in RAX. We check it again. We don't need this. Stuff again. Yeah, we finally need to just generate 0 or 1 being pushed once everything is done. Yeah. I think what we should do here is, okay, so let's do some thinking. So RAX, if it is 0, this is great. We already have it in 0. This one, we should just add another instruction that says move q. What are the instruction coding for this is move q $1 into RAX, because what this is saying is this is the booleanified version of yeah, if it is not 0, then set it to 1 and then move forward. Right. What we'll also do is we'll store the address of this jump. So if it ever skips back, I mean, yeah, if it ever becomes 1, we should jump back to, yeah, if it's, so we just simply test the value now. Right, so we just test the value, and if it's not equal to 0, we jump back, which is this forward jump address, which actually goes to this move 1 RAX, which will jump and then go forward. Okay, this is fine. So these also we can skip out. And it calls get token, stores it. Why is it token and here? What is going on? I thought 12 was OR. Wow, this is really screwed. We made mistakes last time. And so it is already in RAX. So we'll go to next. Next will again parse the next expression, and that will be fine. And patch the target for the forward jump. This is for the final jump. This is okay. All this has to finally do is say that this is a R value. So perfect, right? Yep, this will tell it that this is an R value. Parse expr prefinish. What does this do? Parse expr prefinish. It loads it from this, so we need to store it there too. Fine. Okay. This needs to be patched in the same way. So the pops go away, the test stays, the AL goes away, the PCL goes away, the pushes go away. It just remains JNE. And then we have this one changes. We will have $0 into RAX. Yeah, this is when. Okay, now this is a problem. 0 was a special case. 0 was special because we never had to put 1 into it. We can do it this way by adding. I see. This one actually we don't have to do. This is fine. Perfect. So we test and then we move. Move doesn't set flags, right? Is moving immediate to a register set flags. No. Perfect. So this is good. Okay, yeah. So what this will do is test RAX. If it is not equals, which means it's a we're doing AND right now. Yeah, means it's 1, right? Yeah, if it's not 0, then go ahead. If it is a 0, then it's already 0 and we can just skip forward. Perfect. No, we've already made it 0 here. Damn it. Unfortunate. Could I swap this around? Could I make it? Actually, yeah, I don't need this. What does continue do? Continue does the second expression. At this point, the first expression's value is not going to be used. So I can actually remove this. It also has to return 1 somewhere. Let me think about this. It gets a 0, it skips forward. Yeah, if it doesn't find a 0, non-zero, whatever, that RAX needs to contain the right value, the booleanified value. Yeah, it was fine for OR because what happens is after the second or third expression, whatever, like after the couple of expressions have been done, the RAX, if it's 0, yeah, like when it reaches this point, test RAX, if it's it generates this jump, which is fine, and if the next expression is not an OR, which is where we are done, the value is already 0, so that's fine. At some point it will either find a 1, which will cause it to jump here and then skip forward, or it will run out of the expressions, which will eventually have 0 in the RAX, which was fine. The issue here is 1 is a special case. So fine, we will do both the jumps then. We will have to do both the moves. Right, this needs to be handled a little tricky, but this is what it is now. So what this will do is it will set to 1 and then continue. Actually, we don't need to do it for the first one. We only need to do it for the other ones, right? Because we are for sure that there's an expression after this. Yeah, so we can skip for the first one. For the very first one we can skip. For the next ones we can't skip, because the value needs to be booleanified after at least one of them. Yeah, okay, so yes, pops go away, test stays, this goes away, and now we get here a move. Perfect, this goes away, and then we simply get a jump on equals. So what this is doing is, if it's 0, then we can skip forward, which goes back to storing 0. Wait, hold up, and we don't need this. It's already 0, right? Test rex, we don't need to put 0, it's already 0. Even better. Okay. This moves 1. If it's 0, it just jumps to this jump, and then we are done. If it's not, then we have 1 in it, which is perfect. Okay. And these are okay. I did not anticipate struggling again with the same short-circuiting issue. And then these seem fine to me. It calls get token, checks if it's and if it's not, it goes back, and this seems fine. And we just need to move $0 into -48 RBP because that's what returns, and that's it. This is easy. Okay, now we just need to encode all the instructions for both of them. So move L x30 8548 into R14. Actually, how many bytes are these? 1, 2, 3, 4, 5. Oh, annoying. Wait, we haven't done the first part yet. Sorry, let's do this first. I need to encode this first. Move 1 rex. Yeah. Wow, this is a huge instruction. What's the easiest way? I'll do ex, it's fine here. Yeah, because setting ex clears sets rex too, so we are fine. Okay. So how many bytes do we have? 1, 2, 3, 4, 5. Oh, now this changes. This is not 0, 5 anymore. So skip over more. Let's just skip over how many? 6 instructions? Is that fine? Yeah, I'll just do this properly. When did I test this? Yes, sir. Let's just write it out properly. Okay, so and this is forward jump address, and then we have a few NOP JNE forward jump address. Okay, continue is already defined. Yes, I did have this. Jump on equals, right? And then JNE. Okay. God. Okay, so jump on equals to continue. So if it is 0, we are doing OR, then it continues, right? And if it's not equals, it jumps to forward jump address. Okay, so it's fine. What is next? And this is for ORs. We don't need this. So that was for AND. Okay, jump on not equal. Okay, yeah, this is correct. What the hell is this? Okay, 4885C0, then 740C because we're jumping over bunch of instructions. Oh wait, no, we changed this. Oh god, I hate myself. Okay, so 4885C0, 074A, and then B801000, which moves 1 to EX, and E902. Oh yeah, no, this is just going to be E900 because it depends on how much we're jumping forward. That's fine, this will be patched. And then we have the continue. This will be JNE, which is already correct, and these are fine. Okay, sorry, this took a while. Now, how many bytes do we have to write first? This is 1, 2, 3, 4, 5, 6. I can do 4 and 2, it's fine. Oh. Yeah, I can do 4. 0x74C08548. R14. Now we do 2 more bytes. Move word 0xb a0a into 4% R14. Now we had to store the address of R14 somewhere, right? So I'm going to fix this first. Q6. I remember. Yeah, so we stored those bytes and then we stored the address in the. Is it the start of the instruction or is it? Oh god, I don't remember this. I should have kept the old comments. I don't remember if like the address we're storing is the start of the instruction or are we storing the start of where the patching needs to happen. What would old me do? Oh wait, there's only E9 after this, right? Yeah, okay, let's do the reverse engineering, right? So we 16 R14, we stored R14, and then we immediately stored E9. Oh, so we actually stored at the end of the instruction, not even before, because if you look at it, yeah, it's actually the end of that instruction. Oh yeah, because it's where to jump, right? This is not the address that we have to patch. This is the address where we have to jump. So this is literally the start of the next instruction, which in the previous case was E9. In this case, it will be the start of this instruction. So we have already stored 1, 2, 3, 4, 5, 6, right? Let's do 5 and this separately, I guess. So let's do move B and then do A. Yeah, this finishes the first instruction. We do 5, then we do move Q percent R14 into minus 40 RPP. Okay, this is good. And now we do the 2 instructions. So this one is just move B again. Yeah. Then move L$0x1 into 1 of percent R14, and then we simply do we first do $0E9. Yeah, we have to store this address too. I guess in the previous case it was the same. It was the start of that instruction that we had stored into R40. Okay, yeah, the previous one, the patch address in this was the same. We'll have to just do a small like math later because we have 5 more bytes here now. Yeah, so R40 before was the combined instruction. Okay, Yeah, we had to only store it once because um, both the addresses were the same. The address to jump to and the address to patch later, they were the same. So yeah, okay, this is fine. So move the E9 into how much? 5 of R14, right? Because 5, yeah, okay. And then 1, 2, 3, 4, 5. So 5. 10 bytes total. Yeah. Okay, this is done. I can remove this. Now, let's go to the next one. Okay. So this doesn't need all this anymore. This is not. Oh, this was probably fine. Right? 0C8548. Yeah. Okay. Yeah. So this requires some math to be done. Okay. So what this is first doing is 850F. That is correct. Then it loads R14, it shifts R14 by 2, then it brings back the address that we had stored, okay, and subtracts. I think this is exactly the same. Okay, this is fine. Patches the address. Okay, nothing to be changed here. This is fine. That K is a bug in Vim, don't worry about it. Okay, so this is fine. And then finally the patch, the forward jump. This needs to change. Okay. So we take R14 into RAX. We move. So I think the only difference that needs to happen is the value needs to be subtracted by 5 because we've only added another instruction in the middle, which is like a 5-byte instruction, right? Up, yeah, so we just subtract the value by 5. And it's written here, right? We're subtracting 5 here just to subtract 10. This should be fine, I think, because all we have done is move the patching. Yeah, the patching address is now 5 bytes ahead of us, so the relative jump would be 5 byte less. Oh, but then we also change where it's being stored. It's not being stored at this anymore. It will be stored at this. Perfect. Okay, this is good. Let's make the same changes for OR. And sorry, that was OR. And I hate this. Okay. Oh, this actually surprisingly doesn't change much. So we just have test RAX, RAX, JNE, and no move. Okay, so this is fine. This is gonna stay the same. You have to generate code for this. Okay, so nothing changes on this one, right? Yeah. We can generate 1, 2, 3, 4, 5, 6 together. Now we can. Okay, so let's do 4 and yeah, and we have to do 5 first, and then we have to store the address. Okay, let's do 4 and 1 then. $x75C08548 into %R14 P0x0x05 into 4 of R14 Q5 R14 into R14. This is fine. Now these go away. The value gets stored. Then we move E9 and we incremented that 5. Perfect. 11 calls 10. This is fine. Okay, so we don't need these, but we need, and we already have the instruction for this, so that is somewhere here. Okay, and this just goes back. The math is entirely the same. So okay, let's start by doing, we can do this as 4 4. Okay, okay, so the previous one, okay, the difference here is now this one. Okay, we will fix this. Actually, no, I can keep this the same. So I can say move B. What is it? These two values, not move B, move W. Oh, we already have these. Okay. Actually, let's just use these, right? So we load the values, then we update R14, we move the value out, do the subtraction, nothing changed to change here, this goes stored and this is fine. Okay. Call get token, this is fine. Da, da, da. This works fine. Okay. I think we're done with AND. Great. Now the only thing that remains is function calls. And some of the statements also need to handle stuff, but that should be easy. Export global is fine. Function call expression. Okay. So function call is actually easy. We just keep on allocating stack slots and keep putting on it, and then later move them up. Hey, thanks for subscribing. Hey, I don't know if I recognize you or if you have been here before, but thanks a lot for joining. We are optimizing some of our code generation for the compiler, specifically getting rid of the whole. Oh no, nice to see you again. Sorry, I didn't recognize you. Yeah, so what we are working on today is we're optimizing the code generation that we did. So far, we have been doing like a stack machine kind of code generation where every expression pushes the value on the stack and then pops it from the stack and keeps on generating it. And there was a lot of unnecessary push and pops because of that, and also because of how we handled L values versus R values. And optimizing that, now converting the whole thing into just moving everything in registers as far as possible, and only when you need to like make space for the second argument. I push it onto the, instead of pushing it, I'm actually storing it into a pre-allocated stack slot. And that will hopefully make the whole thing much more optimized. And we do have a sort of a benchmark, quote unquote, of Fibonacci, and we're trying to get it to be better. But yeah, let's see. We are almost close to it. We are just finishing our function call expression, and then we would be done with all the optimizations. Okay. So -8 RBP holds the number of arguments. The unfortunate part about the way this is again being parsed is, ideally I would want to like parse the expressions from right to left and put them up, but we can't because actually function call doesn't need to change, because function call already needs to push arguments in the stack. So we actually don't have to change much for this, except for the fact that the sub expressions would not push the value, just have to push them. That's all we have to do change wise. So this is actually very easy. Yeah, so what we were earlier doing is, for next argument, we were just doing a pop RAX. Instead, it now just becomes push RAX. Yeah, that's the only change. So the difference was, when we were passing an expression, that would put the value and the address on the stack. We just now have to, this time it does nothing. We just have to ensure that it's an R value and push it on the stack. So we simply say, so let's do parse function call expression sub. Let's actually start, see where this was called from. Parse function call exper. Yeah, here. So we have already parsed the first expression, right? Which was, yeah, we call parse expression pre-0, which will get the first identifier, whatever, and it checks if it's okay. So before we do this, we have to so precedence 1 is just function call for us. Yes, nothing else right now. Okay, so the only thing we need to do is make sure that we're not clobbering the L value, the value category of the expression. So this needs to somehow be stored. I don't want to store it in any other register, because get token does mess with a lot of registers, so we shouldn't do that. I think this needs to be allocated on the stack now. Okay, how is parse exper pre1 being called? Yeah, here. So it literally calls it. So we can do, yeah, we can set up a stack frame here. Okay, let's leave a comment here saying -8 of RPP is left expression value category and stack slot. Yeah, the function expression itself, we can, it doesn't really matter. We don't need a stack slot for it. That's okay. Okay, so this calls pre-expression 0. Let's make sure that this has leave here now. Great. Okay, so we call this. Now let's store the value category into it. And before we leave, we also need to restore it in case we did not match a function call. Yeah, So the convention we're following is every call to parse expr returns the value category of the expression it has generated in RAX. So we'll know if it's an R value or an L value in the compiler itself, instead of having to defer this to code generation into the into generated code. So this generates, this is fine. It'll check if it'll get a token. It'll check if it's an L parentheses. If it's not, it will return. Let's go to parse function call expr. Okay, so this one, and this jumps to parse expr pre1 continue for some reason. Which is correct. It does. Oh, it checks if there's another function call again, because this could be recursive. Yeah, okay. Yeah. Eventually it will not be. Okay. Okay, so let's start from here. We have set up the stack frame. So we do get token, consume the RAX. If it's already an R parentheses, then we just go to call expression end, which goes here and generates the whatever actual function call. This has leave red queue now. Okay, this is perfect. Okay, so if not, okay, but this currently the expression itself is an RAX. So we should ensure that it's pushed onto the stack. So we do move. Oh, we have a secondary stack slot being set up now. Unfortunately, we don't have the yeah, we could just move it here, right? Sorry, oops. The other way to do this is we don't actually set up a second stack frame again. Yeah, it's almost like calling the function. Yeah, it's fine. There's like the handling of the function is different versus the expression. So this is okay. It's not too bad. Okay, so I'm loading the load the value category of the expression, the call target. Actually, we don't need the value category of the target itself, because it should be an L value. Yeah, there's not much to do. We don't have to do an N value to R value conversion, so this can probably be skipped. Okay, it must be an L value because it's a function call. Okay, so just simply let's generate push QRAX. Yeah, which is 58 if I remember correctly. Must be some 50, 0x50. So that's what we generate. I keep hitting the caps lock today for some reason. Push the call target to the stack. Okay, so we have pushed the call target, then we call get token and check if it's an R parentheses. If it's not, that's fine. Then we pass the expression. Now for this one, we have to ensure that it's an R value. So we do, yeah, all the expressions we are doing should all be L, and this just becomes push RAX because arguments need to be pushed, not pop. Okay, this is great. We store it. What is this for? -8 into -8 RP. Oh, this is the number of arguments. Okay. Then we call get token, check if it's R parentheses. If not, we go there. And then finally, we have the function called expr end. So this loads the number of arguments. No, this loads. Yeah, number of arguments. Okay, yeah, so it loads a certain number from RSP, which is the call target. So that this should be exactly this. There's nothing changed here. It patches it in. Finally does, what is this adjustment of RSP? Why does, oh, this is after the call has been done. Okay, yeah, this is the actual call. Then pops back all the arguments and then finally pushes RAX. This is not required because the argument is already okay, so we don't need this, we don't need this, we don't, it just becomes 18. This is done, and we need to ensure that the value category of this is R value. Okay, so this will jump back to here. This will go to parse expr pre1 continue, which will then again call token to check if there's another one. Okay, so instead of doing this, should do okay, yeah, this is correct. I think that handles all our expressions. Let me check if we have, yeah, the push null pointer macro is never being called, so I'm actually going to remove it. Okay, I think the only place that needs to happen now is return statement. So what this used to do was just pop. I think this just goes away. We don't need to pop anymore. The result must already be in RAX. Oh, the only thing we need to do is ensure R value. Yep, that's it. And then consume this. Right, this is easy. Generate function body cleanup. Function body cleanup already assumes it's in RX. Okay. Expression statement also just calls parse expression and then does nothing, right? Yeah. And it doesn't matter if it's an L value, if it's an R value, we're discarding the results anyway. So this is fine. Oh, statements, if statement need to handle. Okay, so this is actually pretty easy now to handle. Just these things go away. Right, so yeah, so these two go away. All these need to be adjusted. Okay, Fine. This becomes 0, this becomes 1, this becomes 2, this becomes 3, this becomes 5. Because we don't have to pop anything anymore. The result is already in array-x, except we need to make sure that R value. Yeah, okay. So we passed an expression, we ensured it's an R value, which means it's an array-x. Then we did test, which is this one. Okay. This moves the jump address into RBP. All this is fine. Pass statement block is fine. And this one just generates a jump to end. This is also okay. There's no push or pops. Pass statement blocks is fine. Yeah, all this is good. Okay. And then loop. This is for loop. Needs to be the same thing. We just remove these push array-x. Just make sure that we have R value. These need to be adjusted. So this becomes 0, 1, 2, 3, 5. And the rest remains the same. This goes away. Jump back is fine. Alright, I think we're good now. By statement block, there's no more code generation from here. Oh, there is one more. What is this for? Oh, variable declaration. So what variable declaration does is calls parse expression, calls ensure R value. It's already in array-x, so this can, let's fix this. So minus 8 RBP into RBX. This goes away. This becomes 0. This becomes 3, and this becomes 7. Right, 1, 2, 3, 4, 5, 6, 7. Perfect. Okay, this can go over. All right, I think we're done. We'll try. Okay, a bunch of things to fix in parse expression. Parse expression 33. Yeah, I forgot a bunch of dollar signs. 5493. $256, 257, 256. $267. Okay. Oh, this is not too bad. Get stack slot. Current function slots. Oh, it's not defined here. It's not global. Okay. Parse expr pre next. Parse expr pre next. Get value from stack. It's not get value from stack. What is it called? Get value from dash. and then finally ensure R value needs to be global. Okay, I think that solves all the issues. Now let's just actually test if anything runs, and it doesn't, because okay, let's check if things that work. This doesn't work. Oh god. Valid expression of precedence 0. But does call work? Okay, actually, does empty work? Suck faults. Okay, let's start with empty because empty is the easiest to debug. Does call work? Probably not. Yeah, okay. Good thing we have GDB. Let's start. No. I think we can just do. No, like, how do you start and stop? GDB break at program start. Start I. Okay. Okay, this is main. Look, at least our function is so much more compact now, which is great, because we don't have all that random pushing and popping. But let's pull up what this is supposed to be on the side so we can match it. Okay, so what this is doing is it's loading bar, setting bar equals to foo plus 12 and then returning bar, and foo is set to 13, so hopefully that should be okay. So first it sets up the stack frame, push RBP, RSP to RBP, so this is fine. There's no local variables, but there's one intermediate that goes into -10 RSP, that's okay. Okay, so first it loads the address of RAX and then stores it into RPP. Okay, so it loads the address of foo, stores it into into -8 RPP. Okay, then it loads second one into RAX and stores it. Loads it. Okay. Why am I keeping spam? Okay, then this loads the L value from the first one. Why didn't we do promotion before stashing it? Should have been easy if I'd done the promotion right away. It's okay. So I'm loading the address of the first one. Oh, actually. This is storing the overwriting the second. Oh no, wait. This was the assignment. So this is address of bar. Okay, so there is a problem here. When you're doing get stack slot, it's overwriting the same stack slot. That's the problem. Why is it? Did I not increment? Okay, so this is the problem here. Okay, so what this is doing is, but let's see what this is doing. It's loads the value of foo, immediately converts it into an R value, then stores it into RBP, then where is the addition? Boy, the addition is gone. Oh, it's here. Huh? 12 is being loaded. Okay, there's something definitely wrong with this. Okay, I'm gonna quickly take a bathroom break and I'll be back in like 5 minutes. I'm drinking a lot of water. Alright, I'm back. Also, I just realized today is Spy Day. That's 14th March. This is when also MIT's undergrad acceptances go out, I think. Correct me if I'm wrong. So, big day for some people. Okay, I think what happened here is one, the addition instruction never got written, which means there's probably like some update to R14 that I missed. And so it got overwritten. But let's just try to break this down. So loads the address of bar, okay, stashes it to RPP. First of all, it's the same RPP, but it's okay. And then loads the address of foo into RAX. Converts, loads the value of foo, and then for some reason puts the value of foo into the stack slot again. Okay, that's fine. The value of RAX goes into stack slot. Okay, that's fine. The value of foo goes into stack slot. That's okay. And then also stores the same value at RBX. This doesn't make sense. First of all, RBX hasn't even been set yet. And then does RBX to RAX, which is weird. Does RBX to RAX and then moves 12 to RAX. Okay, I'm going to try a simpler empty, which simply does let's call this main 2, so this doesn't interfere, and let's simply do main. Let's go back to the basics. Just a simple main function. That is also seg faulting. Okay, this main is the smallest function I've ever seen. Okay, so what's happening? One here is I'm trying to dereference an integer. That's wrong. This can be quickly fixed. It's possible that the integer expression is returning an L value for reason, and the return turns it into an R value, tries to turn into an R value and then fails. Okay, so this is easy to solve. Let's fix this first. I'm going to quit this. I need my full screen. Okay. Parse integer expression. Or somewhere along the way it gets converted into an R value for some reason. Okay, so this one is saying it's an R value. For some reason along the way it gets converted into, I'll try to double dereference it. Test RAX. If it is 0, just directly go to end. If it's not, then generate the code and then set it to 1. Okay, I'm going to step through this. To remove this so that I don't have to debug this, and I'm going to first make Let's just check ensure R value. Okay, the first time it gets called is from parse return statement. Perfect. So this, like, it literally doesn't have anywhere else parse R value being called, which is great. This is exactly what we expected. Well, what is the value of RAX? One, which means it's an L value. Somewhere along the way, it got set to 1. Okay, let's parse integer expression. Just step from here. Okay, so parse integer expression, step instruction, step instruction, step instruction. Okay, so now RAX is 0. It goes to parse expression pre-0 continue. Just pre-0 returns. Pre-1 stores the value into -8 RBP, whatever this is. So we can just go next over this. It's not gonna be a function call, so it's gonna call return token. Return the value from RBP into RAX. So let's do 0. Great. This is parse exp pre2 not star. It's not a star expression. Great. Returns. This one stores again. This is parse exp pre. It stores it at -30 RBP. Yeah, it's 48. That's right. So step. Then it does a bunch of stuff. Does a bunch of stuff. Binary operator would say, yeah, it goes to finish, returns. So after this, it should be 0. Great. 0 is our value. And we step. Oh god, there's gonna be a bunch of pre's from this, but it's probably okay because we can just do next high. Yeah, there's going to be like a sequence of precedence. Every time like we reduce the precedence by 1, it's gonna do this. It's one of the handling. I think we'll eventually reach 12 and then 13 and 14. That's no 11, 12 and 14. One of them must have made a mistake. I can try to finish, but this has never worked. Like it somehow crashes if I try to finish. Our GDB like has, okay, so it reaches 14. Oh, how did we reach 14 directly? What happened to 11 and 12? Okay, what is... Oh, here, parse exp pre. We never stored the precedence here. This is in parse exp pre 14. Okay, I guess that's the reason. Let's check what it is, at least to make sure everything is okay. Till at this point, it's okay. Right. We should have saved it in pre 14. Parse exp pre 14. Stack slot for the temporary. Yeah, that's fine. So we should immediately stash it. Okay, so now it's in, no, .sp. Great. Now we call get token. Okay. We do a bunch of stuff. Oh, amazing. One is always returning the wrong value category. Okay, this was simply the reason. Okay. It's not always an L value. If it's an R value, then it's an R value. Okay, so this one, what this is saying is pre14 end. Yeah, so the moment we get the first expression, stash its R value, stash its value category. If it is an assignment, then that doesn't matter. Then we can replace it with the stack slot. Otherwise, and then yeah, and if once the assignment has been done, set it to 1 again, and then finally pop it. Okay, this should fix it. Okay, that ran. And that is correct. Okay, so now let's restore our empty example. This one is still seg faulting. Now let's check what's wrong with this. Okay, it's still jumbled up, but okay, we can try to fix this by changing the example further. Okay, let's change this to just be this return bar. Okay, this ran wrong. No, bar was 0. Let's try to do foo. It's okay. This is one is going correctly. Is this going to work correctly? Nope. This is wrong too. Let's do. It's probably some. I just found out that int division by 0 on ARM64 doesn't trap. Well, that's. I mean, there's probably a flag for it. Like, at least x86 has a flag where you can, for floating point operations, you can turn on or off what the behavior of floating point division by 0 is. You can either set it to nan, or you can set it to inf, or you can set it to trap. Maybe there's a flag for it too, and I don't know if user space programs are allowed to control that, but yeah. No. I don't mean a flag to tell you whether it's a error. I mean a flag to change the behavior of what happens when there's a division by 0. x86 is a flag that you can set which decides whether it should trap or whether it should. And it's very handy because if you're trying to like debug some program that has a lot of floating point math and somewhere a nan get generated or an inf get generated, it's hard to find where it starts, right? So what you can do is you can set that flag in the beginning of your program, attach GDB, and then just start debugging. And then whenever the first like inf or nan get generated, you can actually just know. That comes in very handy. I've done that in the past. There's like a C function also you can write. It's like just an inline ASME one that just sets the flag. And good thing is like it's set from user space, so that's good. Okay, let me step to this and see what's happening. So very small main function. I'm happy about this. I think all that is happening here is the add instructions bytes are not getting generated because it's getting overwritten immediately. So I think what's happening is our binary is per 3. Yeah, here. I think what happens is when we write the instructions at the end, we just don't update R14 properly. I'm using move SB for this. So yeah, here I am moving RDI to R14, so this should update. Like this should generate the right instructions. Maybe RCX is wrong. 16 RAX. Let me check. So there's plus here. So we have, this is 0, this is 8, 16. Yeah, so 16 has the number of instructions, and then I have the actual instructions, and then I have a space. This should work fine. Wait, is it possible that some of my instructions are like disaligned to this point? So we have long, which is 4, plus space is 610. This is correct. We have quad, which is 8, and then space, that was wrong. Yeah, I think this was causing the issue. Token percent has quad and short. Okay, so no space. I used ChatGPT and it was okay at helping. I've been messing around with x86 recently. I had a patch an old game to work on my Mac. Very satisfying to see the game pop open. Huh? Nice. I mean, please do share details about what game it was and what patch you had to do. I mean, I learned x86 first, so that's all I know, and I'm slightly more comfortable with it than ARM. And as a compilers person, I should know all of them, but you surprisingly right, not too much assembly as a compiler engineer. Turns out the problem with the game was that launching in full screen, so I had to flip it. Oh, I see. Nice. Token miners. You can also do that by intercepting its calls to syscalls. Like I'm sure it must be calling some function for doing the actual windowing or whatever, like screen thing. And if you had just LDP loaded it, it might have worked too. Like you just catch all its calls to those functions and then just swap out the arguments before actually making the system call or the function, whatever it was doing. But yeah, patching of the instructions also works. Okay, this is 4 plus 6, this is correct. 8 plus 2 is correct. This is 9 plus 1. Yeah, these are all correct. Okay, so this was the issue. Oh, everything surprisingly compiled just by changing one. Wait, this is insane. Oh, because some of the expressions weren't matching now. This is amazing. This just surprisingly ran. Okay, some of them are still segfaulting, but this is great. Oh wait, factorial is segfaulting, that's okay. Let's check what MT does now. Okay, so there was no issue with our parser. It was an issue with the table. Okay, this is still putting 25, 12, which is wrong. Let's try to debug this. Okay, we at least have our add instruction. Wait, what is the semantics of add? Does it store it in the source register for some reason? I'm going to hate this if it's in the source. Yeah, it's in the destination operand. Destination equals to destinations plus source. So let's see what happened here. Okay, so we have minus 10 RFP into RFP. Okay, this is fine. We moved the address of bar into RAX. We loaded the value into RAX. Then we stashed that value into RBP. Then we moved C into RAX. Oh, wait. This is wrong. Wait, did I? Okay, I think I know what happened here. Get value from here. No, wait, what? Wait, 48. There's an extra byte here. 48. Yeah, this is just wrong. Okay, this is correct. 488B 8D. This B and 8 are a little hard to see. Okay. Still 12. What the hell, man? Okay. But we're getting close to debugging this. So I'm just reading through your messages. It's a very old Windows game that Wine doesn't like on my Mac, so it's a very old text call which ChatGPT was able to decode for me. You would see. I see. So it wasn't really a LTP load thing that you could have fixed. Okay. Okay, now it's loading correctly, but it's loading it into RCX for some reason. Why is it loading into RCX? And instruction encoding is completely screwed. 8B 8D. Okay, I'm going to write this. Okay, minus 24 RBP into RPX. It should be somewhere, right? Plus 24. I added it today. Yeah, here L value to R value. Yeah, this one. Move minus 36 RBP to RBX. Okay. Here. What the hell? Yeah, 488B 8D. 5D, not 8D. No, 8. Wait, 8. I do need it to be 8D because 8B. I'm gonna ask Gemini to encode this. Can you encode move offset RPP into RPX where offset is 32 bits? It's 90, of course. Yeah, okay. I thought they would be the same. This is on me. Okay. $25. Yeah, okay, this is working properly. Now let's change this to be what we originally had. There we go. Everything works. Now let's do make run. I guess we still have some seg faults, but that's not too bad. We can fix this. Like, what's the simplest one? Short circuit has a seg fault. Oh, somehow putchar worked correctly. It printed hello world and then seg faulted, which is interesting. Hmm. Maybe it's the return statement that's causing issue. Let's just check putchar. Yeah, it printed hello world and then crashed. Interesting. Oh yeah, this is our main function. So what is this doing? It just has a bunch of actually let's just do continue. It doesn't show me where the break seg fault happened. Okay. I'm guessing these function calls are going to be fine. Was there a push? Okay, yeah. So it pushes the function on the stack. Great. Then moves the value into RAX, pushes it onto the stack. It's fine. Loads the value of the function target from this. Yes. Calls RAX. Then wait a second. This is putchar, is it? Yeah, this is putchar. I finished this. That's finished. Okay, why is it 18 RSP? Okay, so we pushed. Okay, so here we pushed the target. We pushed the first argument. For some reason, this is minus 18. So it's like clearing up 3 arguments. It should only be 2. Yeah, this math is wrong. Okay, let's check why this is wrong. Function call expression. Okay, this is the subroutine. Here's the last patching. Oh, because of the return values. Yeah. The function. No. The return values are still not on the stack. Yeah, I don't know why this is subtracting. So every time it passes an argument, it adds 8 to RBP. Wait, these values should be exactly the same, right? The value we're loading this Rx from and this. Yeah, these should be the same. Yeah, these numbers should exactly be equal. Why are they not? Also, is this correct? Just move 8 RSP into RAX, correct? x86 64 after a push, does the RSP point to the pushed value or the next slot? Points exactly to the value just pushed. Okay, in x86 after a push instruction, the RSP pointer points exactly to the value you just push. Is decrement before store. Okay, it's decrement before store. Okay, so this RSP is already pointing to the argument. This is the next argument on the stack. This is correct. Why is it 18? Okay, this is a problem. Yeah, this 16 is the issue. Why is it 16? Why is it not 8? Oh, because of the arguments. Yeah, we never popped off the uh yeah, okay. Yeah, there's the dereferenced value of the pointer on the stack, which we previously had. Now we don't have it anymore, so this should be fine. Okay, so hello world works fine without segmentation fault. Factorial also works fine without segmentation fault, but is that correct? Thought factorial is supposed to have done 13 or something. Factorial of 5. Yeah, this is wrong. It just printed the value of the argument on the stack. This is also an issue. We will fix this. So factorial is wrong. Fibonacci crashes. Put caris crashes. Short circuit also crashes. Okay. Let's check why. Okay, did we actually clean up correctly? So yeah, we never did a push. No, we don't have to do a push. The value of the return value must be in array. Actually, just set it to 0. Okay, this is fine. Now let's look at the code for factorial. Yeah, it's just 3 function calls. It's so much easier to debug now that the code is small. Okay, so this is the argument of the first function call, which is the putchar function call. This is pushing the argument of Fibonacci. Then this pushes 5, the argument. Then it takes the address of the function to be called into RAX, calls RAX. This is correct. This we can just finish, hopefully. It is 5. So that itself is wrong. And then this one just fixes the stack, then pushes the return value on the stack. Then rest of this is okay. Okay, so factorial itself compiled wrong. Okay. To debug this call. Okay. God, this is a long function. This is a long function. This is factorial, it's not at least multiple. Okay. So it loads -20 RSP into RSP, which is correct. There's occupied space for 4 local variables, that's fine. Then it loads 10 RBP into RAX. So this is the argument, right? This must be 5. Oh. For some reason it thinks that it's a L value. Oh, which it is fine. This is okay. Here it should be 5, right? It is 5. Next, perfect. We load 0 into RAX. Fine. We move the old value. We load the old value. We compare RAX, RBX. Set equal AL. Move. Okay. At this point, they should be not equal, right? So this should be 0. It is 0, perfect. And then jump on equal, which means if it's 0, jump. Wait, how bizarre. This is... Oh, I think I forgot to increment the counter for this jump. There's supposed to be a jump here. Move 1 and then jump. Yeah, there's just some leave red here. Where did this come from? Oh, no, this is fine. This is just generating the code for if it is true. No, but this is not how it's supposed to be generated. Is this a simple if condition or is this a... Oh, it's just 0. Okay, there's no or. Fine, this is fine then. Okay, this is okay. Then this one just moves the factorial target again, pushes into RBX. Okay, this one should do the -1, right? Okay, there's some garbage here. What is this SHRD coming from? Okay, we will fix this. So there should be 4 now. It is 4. We do ni. Okay, this is great. Cannot insert breakpoint 0. I don't know what this is. is fine. So for some reason it's returning 4, but that's okay. Stores the result into 18 RBP, okay. Then loads 10 RBP into RAX. Oh, this is the argument. Yeah, this is just the multiplication itself is wrong. I think this the multiplication code is wrong. Okay. Okay, so we have 4 bytes of instruction. Let's check what this does. It's probably just I think I just got the arguments wrong, or the encoding wrong maybe. RAX equals to RAX times RBX. So this is fine. 480F. Wait a second. Why are these flipped? They should not be flipped. Are all these instructions wrong? Oh god. And how is add working then? No, this is fine. This is okay. Okay. 480F AFC3, not AD. $120, yay. Okay, this is working fine. Let's check Fibonacci. Segmentation fault, okay. But let's test the other ones. Short circuit is still failing. Factorial is producing the correct result. Fibonacci is failing. Let's do short circuit first. Yeah, it's possible factorial and short circuit have the same issue because factorial Fibonacci also uses short circuiting. Yeah, it has this x equals 0 or x equals 1. So we need to just fix short circuiting. So the short circuit it has 1 or 1 and side effect and 0 or side effect. This is normally supposed to return. So 1 or itself should just stop because 1 or anything else is 0, no 1. So this should just return 1, right? There should not be any side effects. Okay. Well, example short circuit. The fact that it's okay. Okay. So setting up the stack, -8 RSP into RSP, move 1 into RAX. This is correct. And it immediately lies to dereference. So this is wrong. It's because when I'm doing the ampersand, it's probably clobbering the value category of the sub expression. So let's do parse expr pre 12. Yeah. Here. So where was pre 12 called from? Here. Okay, so parse expr pre 12, before we call that, we immediately store the value into -48 RBP. This calls get token, does blah blah blah. Oh, here. Yeah, you need to ensure that there's like a bunch of stuff happening here. Okay, so this will do ensure R value. This is fine. I think this from here it's all okay. Just need to make sure that this also goes into 11 because 11 would make the same mistake. Oh, 11 never did. R value. Another bug, but okay. This is solved now. Oh, this also needs ensure R value. Yeah, how did we miss these? Right, when we call the second one, it needs to be turned into an R value if it's an L value. So this goes here. Okay, factorial is running, which is a good sign. Still running pretty slow though. Is that correct answer? And everything else seems to be correct now. Is this correct answer? Sorry, Fibonacci I meant, yeah. It is correct answer, okay. Let's time this and see if we have any improvement. This still runs very slow and would be very sad. Okay, it barely got down from 6 seconds to 5.97 seconds. Actually, no, it was 10 before, right? Let's compare with our GCC-00. Time it. Yeah, it's closer now. It's 5.9 as opposed to our previous. I think it was taking 10 seconds earlier. Yeah, it was 10. So I've reduced the call time into 5.9 seconds from 10 seconds. That's like a reasonable improvement. Okay, there's still some issues, which is probably because of the calls. Like the calls are indirect calls here, which is not great. I do want to verify first that that is the issue. So, how can I test this? There's an easy way to test this. We can do obj dump three b0. Oh, this is wrong. What the? That's not the address of main. Oh, wait, this changed. It is this address now. Okay, this is correct now. So what we can do is we can dump these to a file, scratch diss.s. Okay. Remove all this nonsense. Convert these into instructions, and then go to this address and just call it main. Oh, of course, let's destroy it. Here it is. Let's call this main and then delete everything. Honestly, I can just leave those labels around. They'll just like behave like labels, but it's okay. Let's just, oh god, what did I do? I'm trying to turn this into like a normal executable that I can like debug and measure the performance of and try to like patch, like make manual changes to this and see what's causing the issue. So we remove this main. Okay. Oh no, wait, why do we have these numbers? I just wanted the instructions. Okay. And I'm just gonna call this my start, which we don't care about. And put this inside dot text and then dot global main. Okay, now if I compile this, should open mismatch for JE. The problem is they're not labels. Okay, this is another issue. 247. Oh, these are just. I think I'm just gonna get the address of Fibonacci, then a function of Fibonacci, and then try to patch it manually. Oh god, I hate this. Yeah, this is the address of. Let's generate this again. Okay, so this is the address of main. Should we copy? I'm not going to find it. Okay. Okay, this is the start of. There must be a couple of leaverettes, but yeah. Right, that's it. Why are there 3 leaverettes here? Yeah, I think these are fine. Where is all this garbage coming from? What's the main function? Oh no, this is the main function. What the hell? Okay, so we want, let's put char, this is Fibonacci. I was confused for a second. Oh, wait. Yes, this is the Fibonacci function. Now, where does this end? This is the first leaf, which is the early break. This is the call. This is the call. And these are the last ones. Okay, so you take this out. Scratch fib.s and then try to okay, this is our fib function. Okay, there's like a bunch of jumps, and actually these can work because these are just targets now. Yeah, these will just work. These are just targets. No, actually they won't work because I just need to remove the, let's do a trick. What we're gonna do is we're gonna insert L underscore, so that makes them all into labels, and then we change all our jump targets to be L underscore and remove these. Okay, it's a little bit of work, but it's fine. There's not too many of them, so it's fine. Yeah, this is also okay. This is fine. What was this? This is the call target, I'm guessing. Yeah. Great. Okay, this is our fib function. So let's try to compile this. Oh, we need to remove those extra instructions. Sorry guys, this is taking a, okay, this needs to go away. Why is there an empty what is this here? It's probably just a long instruction. Okay, this seems to be fine now. Let's try to compile this. Yay, it works. Now I need to add a driver. Which is in long Fibonacci long x. So declaration and main printf percent LLD slash n Fibonacci of 43. I think it was 43, right? Yeah. This is basically now compiling our generated code with GCC, but like this will create all the sections and everything properly, so perf can work, and we can also then try to manually make changes to the instructions and see if like we can get it to be faster, which is kind of cheating because we're now testing out optimizations without actually doing them in a compiler, but I don't think it's too bad. That's fine. Undefined reference to Fibonacci. Yeah, because we never called it Fibonacci. Oh, but there's another issue with this. The calling convention is wrong. God, I hate this. Okay, I'll have to write some stubs to call through it. It's not that hard. I'm gonna call it fib impl, and then this is easy. The first argument is in what, RSI. RDI. Okay, so what you're simply going to do is push RDI. That's it. And then call Q fib impl. And the return value is an RX anyway, so we can just do it. This is easy. And this is our Fibonacci stub now. Okay. Okay, this is fine. Oh, bad or irreducible absolute expression. Right. Oh, I didn't give it a name. This looks correct. Okay. Creating DT text rel in a PIE. I'm not complaining. Relocation in read-only section dot text. It's not complaining. Run it. Okay, it runs fine, so we don't have to. Nope, it did not run fine. Come on, don't do this to me. Is it because of the move ABS? No, there shouldn't be a problem. What is the issue really? Creating DT text. Okay, I'm just gonna. DT text rel in PI. This is. Okay. So I'm gonna say F no PIC. You're trying to use the relative address, absolute address in a context with the linker requires a relative address. Move A B SQ into RAX with 64-bit addresses, 64-bit labels. I'm compiling with no PIC. Not using a shared library. Right, you know what I'm going to do? I'm going to get rid of that move ABSQ and solve everything. Issue is these offsets are going to change now. I have to maintain the same length. Yeah, how many move ABS there are? There's only 2 of them. Currently there are at 5 to F. This is harder than I had imagined it to be. Linker input file. Oh. This works fine. Let's do this. Why is it even leaving it to the linker though? Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10 bytes of encoding. If I change this to if I comment this out, and if I change this to %RIP into RAX, we'll have to just add some no-ops. How many bytes does it occupy now? One, two, three, 4, 5, 6, 7. This only occupies 7, whereas this is to occupy 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I'm just going to add 3 no-ops after it. And that should fix it. Okay, and then this same thing goes here too. Okay, so this should be compatible now, right? God. In function is undefined reference to 3315. Oh, turns out this was a required label. Of course it was. Everything bad that can happen will happen. Okay. Finally. Now does this run? Nope. What's wrong with this now? Maybe the set fault was because of something else, not because of this. Wait, why is it running to 2B? Yeah, it's going to 2B. I think it's mainly because of... Wait, what if I do big Fibonacci? Oh. Yeah, I think the call is fine. Nope, the call is not fine. It's somehow returning to 2B. This never happened in my side. Somehow my generated code is working fine, but this compiled with GCC is causing some issues. Oh, it's maybe because of the displacements. Yeah, and the like. Yeah, like these encodings, for example. It's possible these are not 32-bit. Like specifically these ones. It's possible it's encoding it as a 8-bit encoding, which is causing all the addresses to be off. Okay, so this also needs to have 3 more bytes of NOPs after this. And this needs to happen after every move that touches RBP, because we have assumed that our addresses start from like the 32-bit displacement, so this is wrong. Okay, this is also going to change. This is fine, this is fine, this is fine, this is change, this is going to change. This is fine. This is accessing the address is fine. This is, we have assumed 32-bit already, and this is always going to be 32, so that's okay. This is changed. Change. Okay. Hopefully this works. God, this is still crashing. It's some of those displacements too that might be wrong. Yeah. So all the jumps targets also we need to make sure that they are using D32. So let's fix all the jumps first. So this has to be .D32. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2 this one is also .d32. This is the one that just goes over, that shouldn't be d32. Or like for example, this shouldn't be d32. This is a short jump. This one using a short jump. Okay, this is the only jump which is interesting. JNE. J J E J E. Okay, what is this supposed to do? 3315. It goes here. Yeah, this is a forward jump. This is fine. This one is only a short jump. This is from the OR, so this is fine. And then there's no more jump. JZ JNE JNZ JL. Okay, I think this should do it. Wait, this doesn't go with the label, right? What is the syntax in GSM for a 32-bit displacement jump? I think it's jump.d32, not with the label. I have this written down somewhere. Yeah, it's J. Let's hope this works. Oh god. Okay, I give up. I can't get these instructions to produce the right encoding. What if I just... Wait, does it really matter what... Yeah, it doesn't matter how many bytes encoding this is. These instructions should be correct because I'm jumping to a label, right? This should not be required. Yeah, this should not be required. It's failing for some other reason. Okay, I guess I'm just gonna step through this. Yeah, since I'm using like absolute labels, it doesn't matter how long my instructions are. The jumps should all be correct. I have to keep stepping through this till I find the fault, which is going to be insane. Like it's somehow like the return itself is failing. It's jumping to the wrong address. Wait, why don't I do a small factorial? I'm an idiot. I can debug through a smaller factorial Fibonacci very easily. Let's say Fibonacci. Why am I doing 43? Yeah, let's do 2. 2 is one more than the. Okay, great. This is much easier to debug. Okay, this is calling 2. It's comparing against 0. Interesting. It went to Fibonacci and then the return failed. Can I just jump to here? Actually, why don't I go back? Right, so I can put a breakpoint on Fibonacci finish. Okay. Okay, great. We're on the stack. Okay. That seems like a reasonable RSP. What's the value? It is 2. So something is wrong. Okay, let's do something. Break Fibonacci. I already have that. Okay, that's fine. Run from the beginning. Five 513. No. RSP. D 8. This is correct. What is the value? on there is a return value on the stack. Okay, we can just watch this address and see where it gets corrupted. And why this does not matter for the previous cases. Yeah, something is corrupting the return value. Ouch. No, I want to watch the RSP. No, now that. What the hell? Okay, now we do watch star RSP. This will watch the value pointer. Pointer. Perfect. There we go. Found it. Oh no, because the RSP is literally watching the RSP. God, I hate this. We need to copy the value, and I can't copy it for some reason. I have to type it out. How many F's are there? 1, 2, 3, 4, 5, 6, 7. Okay, we have a watch point on that address now. That's because nothing should corrupt this, right? Okay, this is correct. This seems fine. Wait, was that RDI by any chance? Triple E8. So triple D8 is the return address 555 ending in 14B. Okay, so this is correct. Oh, actually, we need to check if any of the previous ones are getting corrupted. So let's just remember what these are. Oh boy, this is gonna be hard. But these all look like stacks. This is okay. We just do ni, and then we do this again, $16 RSP. Oh, we did not pop. This is on me. Wow, this was so bad. This was so bad. This is so bad. I wasted so much time just debugging stuff that did not have to be debugged. Okay. This was so stupid. Okay, this is taking 6.12 seconds, which is what we expected. Now we do perf, and hopefully this works because GCC has put all the instruction information into the executable that perf can access. There we go. Oh God. Every single label. Every single label. Yeah, this is not fun. Okay. Here's what we're gonna do. We are going to add a label, make these labels local. Actually, these knobs can go away. We don't need them. Hopefully local labels won't be reported and we will be fine. Yeah, adding a dot to the label makes it local. And hopefully perf will ignore them. $42.60. It's almost 3 p.m. I did want to wrap it up earlier today. Nope, it's still expanding all the labels. Why is it expanding all the labels? But hey, at least we can look at the hotspots given these labels, right? No fun, man. So the hottest spot is this instruction, which is 3389. Let's see what's happening here. It's probably like a load dependent one. Yeah, it's minus 28 RBP into RPX and then load that, which is interesting because it's just loading from a local stack slot. Guess what's happening is, like, we literally wrote it here and then immediately wrote it back, which shouldn't be a problem. Let's see if this is actually the issue. What if I just made it this here and removed this, right? What this will do is skip that memory load, and let's see if this drastically improves performance. 20% of the performance should improve, right? Because it's something else this time, which is great. Let's time this. What this is basically telling me is unnecessarily using stack slots is causing, okay, this went down to 5.585, which is better than the 6 earlier. Let's do the second one. In this case, it's this instruction. Again, I think it's going to be a load followed by, yeah. I don't know how to fix this, but we will think about it. Yeah, again, it's a load followed by this. And again, this is not required, so I'm going to try to do this. So on the fly optimizations. If this comes down to like 4.9 or something, then we'll know for sure that those stack allocations are the issue. So not this one. Because GCC 0 runs in like 4 point something seconds, 4.5 seconds. Okay, that hotspot is gone. There's another one. Push RBP. Hey, how can push RBP be a problem? It's like, I guess new stack frame setup is always a problem. Okay. This one. Ooh, interesting. The loading of the address is the problem now. What is this for? Move 8 RSP into RX. Oh, this is loading the address of the caller calling from the stack. Oh yeah, maybe we should try to check if we can convert those indirect calls into direct calls, right? And if that contributes to it. So we have these two indirect calls here. I'm just going to say fib impl and fib impl. And because this we can actually optimize in our compiler. .182. Let's try to also do if you don't need this, we also don't need this, which means this needs to be 8. Similarly, we can remove this. We can remove this. This needs to be 8. I don't understand where the bottlenecks are, and then again focus on optimization, but this is just a little bit zero Fibonacci.c Fibonacci dot. Okay, it's 4.337. So there's still some bottlenecks. Let's look at it. What are they doing better? Damn, the function is so compact. It's just this much. So this is stack frame setup. Push RBX for some reason. I guess saving Collie save registers. Subtracted RSP, move EDI. Oh yeah, okay. So the other issue could also be just our instructions being longer because we're doing everything in 64-bit. Yeah, we should actually check if what happens if I make it long, right? Here, we should actually make this long to make it fair. Okay, that didn't change anything, which is fine. Okay, that's fine. I'm gonna make peace with the fact that GCC's O0 is going to be slightly better than ours, but that's not the goal of this experiment. But we did identify some bottlenecks, right? Like the bottlenecks were repeated storing to the stack and popping it back again. Well, not popping, but like storing intermediates to stack causes some slowdown. They actually, I mean, they do it too. Wait, why is this still using EX? Shouldn't this be RX? Can I not compile it again? Wait, what happened here? I changed this to long. Save this. Compile this. Oh, maybe I changed the example, not the right scratch one. Yeah, I think I. Oh yeah, this is the right one. Okay, so this brings it to 4.661, which is slightly larger. And I want to check the instructions now. There we go. Our phone is using RAX now. And this one does use like stack slots for storing intermediates. So RDI into minus 18. Oh, I guess arguments being passed on the stack causes a significant slowdown too. Yeah, because that does create more memory footprint. That's fair. That's fair. Yeah, this one is basically not using uh, any amount of stack space. Everything is going through registers except for this one local intermediate, which is here. Yeah, it stores. No, this one is just the first value, comparison, then jump, comparison, jump. They're doing something similar to what we are doing. Instead of like they have a one move to EX here too. In our case, it's just at the top, so it's actually pretty similar. And then the jump to the final one, which 1 to 1B, which goes here. Oh, that's the final return. Okay, and then 0. Oh no, this one is for the return value. Okay, my bad. So they're optimizing that a little bit, and then subtracts 1 from the value, moves it to RDI, immediately calls it, moves the value into RBX. Yeah, instead of going through this, yeah, so the only value they're putting on the stack is the argument. All intermediates are in register, which is better usage of the stack. Yeah, that's fair. We can't do that right now. We have to be happy with what we have. Yep, at least it runs. Perfect. Okay. I'm gonna do some cleanup and then do pointer arithmetic properly. What order should I do it in? Like right now what's happening is our sub expressions don't have types. Like everything is considered as an integer like thing. We need to be able to like assign types to all our expressions. Like variables have types based on how they are defined. Function calls have their type defined based on the function target you're calling. But that's about it. Everything else needs to be given a type 2, and the way that will happen through is like the parse expression now needs to return the value of that, the type of that expression. um, yeah. So let's do some cleanup though. This parse expression is very cluttered. I want to have like very separate functions that just are together. Like right now they're jumping all over the place too. I want to make sure this is correct. Okay, so this is fine. This is fine. This literally just calls parse exper pre 14. Special case for which checks for assignment. So this one I'm going to keep it. And let's try to make things local too if we can. So let's call this check next. Right? This way we will have okay. This is okay. This is okay. Oh yeah, we have to change the associate of this too. That's okay. This we just call end. Okay. Just making sure that the syntax works. Numerical labels, back and forth styles are pretty. They are referenced using dot prefix label. Yeah, if you start a label dot, the assembler treats it as a local symbol. They're often used for things like end of a function. Yeah, or specific branches of the name function. The L convention labels starting with this are special. The assembler handles them, but the linker discards them. They won't show up in your final binary symbol table. Okay, this is what we should have done to fix the perf issue. We should have prefixed them with capital L, not small l. Boy, okay. Yeah, so this is fine. So R14 is just this one, right? There's nothing going out of R14. Let me just compact this a little bit. Okay, this is good. Now let's do parse expr pre 2. Yeah, this is 14. 2 is what? I'm just gonna put some comments here. Handles ampersand and star. Get token. Dot not amp. Okay, this is also a self-contained function. There's no back and forth jumping. Pre1. Okay, pre1 has some pre0. Continue. Okay, this function call expression needs to be brought here. Okay, we will rename this later. Function calls. Okay. So this one actually, we can merge their yeah, this is this stack frames can be merged. Like this one is setting up a stack frame, and then again this one is setting up a stack frame. So we could technically merge them. What happens to this return though? Yeah. So Okay, let's think about this. So this call needs to not happen, so we just say parse function call expr here, so this will directly jump here, and this goes back anyway, so this goes back. This does move qrax into -8 rpp. I mean, that we did here anyway. This is moved here, this will always be correct, so we don't have to do this again and again. Right. Now, this one doesn't get a separate stack frame. This ends up becoming 16. And this just becomes jump. Okay. This just needs to be adjusted to have 16. This goes here. Okay. Okay, this brings everything together. This is a big change, but I think we should be fine. And we can also make this one local, right? Okay, and then pass expression 0, identifiers and integers. Okay, this is fine. They just need to be moved in here. So these both need to be moved. We have parse integer expr. And so all these are doing is return. So I'm just gonna put return here. these are fine. Okay. Handles all binary operators given precedence in RSI. 2, 11, 12. Check binary operators, fine. Finish. Okay. Okay, pre-12. Pre-12 was actually pretty compact, but this one doesn't require any big changes. I don't know why I keep hitting the caps lock today. Probably the keyboard not placed right. Okay, this looks fine. This is our data. Are you kidding me? So what's the point of local then? The local label prefix capital F. If you want labels to be truly local and hidden from global symbol tables so they don't clash or show up in obj dump, use .l prefix. So they don't clash. However, even .l labels must be unique within a file unless you use a specific assembler trick. The common way to handle reusable labels is to combine with a function name, but tedious. Instead, use numerical labels. Are you kidding me, man? so bad. I'm gonna ask GSM local labels scoped inside function. There are local labels in syntax, but they're not function scoped. You have to use forward backward annotations to reference to them. Well, that was annoying. Okay, I'm just going to prefix everything with the function name too. God, this is annoying. But I'm still going to keep this that way. I don't have to. Yeah. This is what it has come to. Should probably put a dot in front of these two. What is happening? There's a delay in my Vim for some reason. It takes a few seconds for it to appear. Okay. That was easy. Oh yeah, what the hell is this fast expert pre-finish? So this is not being used. I'm using parseExpr dot finish now. Just doing a bunch of things. I guess I should do that too. Check next. These are fine. Okay. parseExpr dot parseExpr 314. And if I export to parseExpr pre-finish. Everything seems to be working fine. Yeah, this looks mostly fine. Okay, I'm gonna make some changes. What's the difference between Makefile and Shadow? Changed implementation to use register instead of pushing and popping on the stack. Yeah, so this is done. Now let's figure out how we can do types. So what I basically want to do is currently parseExpr, the common like top for everything, returns in RAX the value category of the expression. Like currently, hey, I'm returning the L value, basically I'm returning the address of the expression as opposed to the actual expression itself. What we want to do is change this to also return the type, which will be in RBX. Uh, right now, I'm not using the type at all, but it will be used. The the only annoying part about it being in RBX is that it would have to be like, if like, just like we have to store the RAX sometimes before we do the next check, like before we do get token and stuff like that, we'll have to check RAX too. Uh, it would have been nice if I could combine both of those RAX and RBX into the same register. It's possible, probably, like if I can encode somehow the type in the 64 bits of the, like 63 bits even um, of the register, and then use one of the bits to tell whether it's an R value or L value. It could work. The annoying part is, maybe it won't work for like pointer types, and I haven't decided on how I'm going to encode pointers just yet. I don't know if I have a free slot. I think it's just better if we do it in RX and RBX. So I'm gonna put some comment: accepts no arguments, returns RAX value category of the expression, 0 equals R value, 1 equals L value, right? And then in RBX returns type of the expression. And so this type itself won't like contain the value category itself. Like if I have a variable, like say a equals 5, when I parse a, I'm not going to return like int star. I'm still going to return int, because a itself as an expression is an integer. It's the type of it's basically that this expression is supposed to evaluate to an integer, but I'm giving you the address of that integer. That's a separate, like in a separate register. Okay. So the simplest place where we can start adding this is at identifier, right? Because when we do parse expression identifier, these, we know the types of them because it's either a local variable or a global variable, and both of them we have the types recorded. So let's do that. Oh, I should also put a comment here saying in generated code, the expression is stored in RAX. Yeah. Okay. Okay, let's go to the identifier section. Actually, let's look at the identifier table first and see where do we have where's the local table? Local symbol table. I think it's another file, but let me check. There is another file. Here, no. Yeah, here it is. So 24 LTES per identifier index, stack slot, offset, and type of variable. Okay, so check local table is fine. We do identifier. Okay, pass expert identifier, expert local. So this one loads the this one here, it loads the offset into EAX. The annoying issue is this is gone, but we can do this. We can do 16 of RAX into RBX. So RBX now contains the type. Same for global. This one is global symbol table is here, and its size is also 24, and its identifier, code gen address, and type of variable, so it's the same. So this also gets the same code here. Now to make sure that RBX is not clobbered here, it is not. And so then this returns out with the right value. Okay, perfect. Let's handle for other expressions, make sure that at least it's preserved. And then once we get to like addition expression, we can look at this type and decide what to do with it. Currently, we don't have a mechanism for pointers. We need to figure out how to actually record pointer types. Like currently, even the parser doesn't handle pointer types. So I can't write char star. Need to figure out a way how to do that. Any suggestions? I mean, one thing I thought about is like currently. Currently, I have, like, for example, if it's char, right? I'm storing it just as, like, right? I'm just storing it as no, it goes the other way. Values move towards this, so char, right? This is how we are storing it currently. I was thinking we could just like keep shifting it and add like, so like for example, if it's a char star, I could store it as 0000000 char star. The problem with this approach, however, is that I get limited by how many pointer indirections I can have. It's fine, like it's okay to have, I don't know, like how many pointer indirections are these? These are like, so char can have 4 pointer integers, pointer indirections. Int can probably have like a little more, 5, and long will have 4. And the issue is, once I have complex types, it will be annoying. But this is very easy to handle too. Like when I dereference a type to get what type I get out of it, I just shift it by 1. It's like the easiest way to do it. So I don't know how to handle this. Maybe one way I could do this is actually put this in memory somewhere, like the pointer type itself, put it in memory, and then point to that. And looking at like, so either I'll put the type directly into the register like char, or I'll have a pointer that points to a table where the actual type is written out, and then I could do duplication on it too to make sure that it doesn't. And same limits about instructions, like characters can be applied, saying your types themselves cannot be long. Actually, can I put this directly in the identifier table? Like, can I make this into an identifier? The pointer type itself can be an identifier. That might work. And what I can do is all types can be put into identifier table. So that way I don't ever have to like handle regular types and other types differently. Yeah. Like why does yeah, like as soon as I type parse the basic type, because types can be longer than one register, so I can always put them in the identifier table, just like identifier. That will allow me like have 32 characters, which is a lot of pointer interactions, and we don't have to worry about it. The only downside is custom types will have less. And then I also have to think about how to represent function types and array types and so on. I want a better way to do this. It would be nice to have data structures, which would be helpful. Like I could like create a linked list of the type to say like, or a tree of type AST of types to say that this is like a pointer to something. Um, right now, hmm, I need some AST data structure to represent this type, and I don't want to implement a whole ass AST data structure. Maybe I can do two identifiers. Like 32 bits of identifiers for the name, and then I'll allow like maybe another register worth of pointers. How about that? So it will be an index into the identifier table, and then separately. Right, so what I can do is I can have a type table which will have two entries. One is an identifier index or a. Hmm, yeah, it will have identifier index, which will give us the base type, and then a sequence of stars. Yeah, that will allow us to do. I could also change the API to return the type in RBX and RCX, where RBX will contain whatever the type it is, and RCX will contain the number of pointers to it. And we are changing the API a lot, and then this RCX has to be constantly carried around everywhere. It's a lot of work. I was already hating like RAX and RBX. You just need some way to represent these pointer types. Other mechanism is instead of returning the type itself, I can return the size of this type. Like for example, if it's a integer, it will be like 0. If it's a pointer, then it will be the size of the element it points to. And that kind of works for a single pointer interaction, but when you have like pointer to pointer, it becomes hard to recognize like what it's pointing to. Yeah, good way to implement pointers. It's also almost 4 p.m. I kind of wanted to stop early today. Maybe I'll stop here and then think about pointer types a little more before I stream again. Hmm. It has been 6 hours. I have some plans today. I need to be somewhere, so I think I need to go. In the meantime, I'll think of good ways to represent pointer types. Alright, yeah, I think I'm gonna call it for now. Um, and then next time we meet, I'll have a good solution for pointers. All right, thanks, folks. I'm gonna close here now, and then we'll meet next week.